Okay, morning everyone. Welcome back to the second day of the CAPAM workshop on the next generation general tuna stock assessment model. Today we're going to be talking about random effects and in the morning and close kin microcapture in the afternoon. And so we're going to start off this morning with Anders and his introductory presentation to random effects. And so we'll just wait a couple more minutes to allow people to join. And just a reminder, in the question and discussion sections, attendees, put up your hand and we'll give you permission to speak. And we'll have a break around 1 p.m. Between the two topics. Some of the presentations from yesterday have been put on the workshop website. If you scroll down below the agenda, there's some abstracts, and then under each abstract, I've posted a link to the presentation slides there. And also a reminder that the meeting's being recorded, and we're going to post a recording on the website for people to look at later. Okay, Anders, do you want to start us off?
Yes. And you let me know if you can't hear or there's something going on.
We can hear you fine, so we'll let you know if anything goes wrong.
So, dear colleagues, and especially Arnie and Mark, I thank you for giving me this opportunity to remind you all about the essential role that random effects play and should play in assessment models. I should note that I have been up all night doing your meeting yesterday, and I've had exams all day with the students. So I'm a little bit exhausted. So I'm very grateful that you have given me such an easy task for this meeting, because there is nothing easier than convince you that random effect is the most sort of natural tool to use in assessment. At least I consider the sort of task of an assessment very, very that it's natural that we have this unobserved time series. And then in addition to being the natural choice, it also seems to sort of more pragmatically be helpful in solving a lot of problems that are very common in assessment models. So what is essential output of an assessment model? I think that it is to figure out how much the next year will be like the current year, and kind of equally important, how accurately that we can actually make such predictions. So what are these random effects? Well, it's something that's random and unobserved. And so a way to think about it is that it's an observation that we wish we had. And what we would want to observe in an assessment model would likely be the stock sizes or fishing mortalities or something. Even if we observed it with noise, that would be a sort of direct observation of that. So think about it in that way, that it's the observations that we really wanted to have that is affecting the observations that we actually have. In assessment models, they are very often these latent time series of stuff that we wish we had. And we estimate them by integrate over all possible values of those quantities. And there are a few techniques for that I won't go much into in this presentation here. So what is exactly the difference between an assessment model that has random effect and one that does not have random effects? So for students, I normally say that we have in full parametric models, we have two types of building blocks. We have observations and we have parameters. Observations are, of course, random and they are observed. And then we have the fixed parameters that are something that we want to estimate in that sense. In contrast, in the random effects models, we have three types of building blocks. We have the observations still, and then we have random effects or latent variable or whatever we call them. And these are kind of like observations, that they are random and then they are not observed. And then we still have parameters, but we have a few more parameters, possibly, well, we have different parameters. And the one mainly that we have extra is this process variance here that is describing how the latent variables are evolving in time. And my claim is that that's actually a very important thing. And it's kind of essential difference that estimating that quantity is kind of built into the model from the get-go, instead of something we need to patch together afterwards when we have the, let's say, estimates of n. Then we need to figure out what we can expect happen next year, but the model really tells us nothing about that or the precision about that. So let's look a little bit closer into this, what's actually in this sigma process, the variance of the process parameters here. Because the things that are in that sigma process would, now I'm thinking about sort of this the SAM model, but they are sort of similar quantities or in that sense. So we have, for instance, the sigma for recruitment. That's the standard deviation for recruitment, and that's quantifying from the historic time series how variable that we can expect recruitment to be around however we choose to predict it. So that's really an important thing to have when we do our short-term forecast, which is part of what we need an assessment model for. The next one could be a standard deviation for the survival, the survival process in the cohorts in an assessment model, and quantifying how well our stock is actually following that stock equation. And that might be more sort of in a diagnostic capacity that we're interested in that. But if the stock is not really following the stock equation, then it might be that we have defined the stock in a not optimal way, that there's some migration in or out of the stock, or that we have misspecified our natural mortality or something that is indicating that the model structure that we have is not really good at predicting down the cohort there. So that might be the idea for this one. And I claim that that's also something that would be useful to know. And then we might have a sigma describing the selection or the fishing mortality process. And that could inform us about how much we realistically can believe we can change the fishing mortality going forward. And if we change the fishing mortality, for instance, for one age group, how the other age groups might follow along or not follow along when we do our forecasts in that sense. So I claim that these are all things that we actually want to know, and they should be estimated. They should not be decided. I've heard that a lot recently, that well, we can do random effects, or we can do penalized likelihood, and it seems to be almost that is sort of equally valid or equally justified. But I think there is a big difference whether you are actually trying to estimate these things from data, or it's just something that we assign to these things. Then, so this was a little bit of the philosophical stuff. Then there's all the practical benefits. The reason number one is that we can set up these flexible processes with a very few number of parameters. And the one that we started out with was this fishing mortality process that we specify from one year to the next. Fishing mortality might evolve as a random walk, or it could be an AR process or something. And it actually, with very few parameters, is able to match very tricky scenario, even if you try to change fleets combination in a very sort of nasty way to change the selectivity over time, you can look at it and you can see that you can actually have processes like this following it. And I like to think about this as sort of the middle ground between fixed in one end, having the fixed selectivity in a number of years, and then having it totally free. And this kind of gets you an optimally estimated weighted average of the two scenarios, if you will. So it borrows information across year and it doesn't ignore the annual variation. Both things, you get both things at once. But there are so many other processes in our assessment models, and here are just a few. I mean, we have the recruitment, we have the survival, we have the fishing mortality, but we also have the mean weights or maturity or things like that. And these can be cast in a similar way. So it's not just for the fishing mortality that we want this. We want at all places to figure out what's the best combination of borrowing from the neighboring years and taking account of the yearly variation. And this is not exactly from the same model as this paper described, but it's similar. And here you can see these are weight at age over the years. And you can see in the historic period, they pretty much follow the observations. There is a little bit of smoothing going on, but that's probably very reasonable. And then in the forecast period, here we threw away the last 5 observations and tried to forecast. It's actually able to mimic some of the things that happened instead of using, let's say, a 5-year average or things like that. So we get both a smoothing in the historic period and the ability to predict a little bit into the future in this sense. Then there's the recruitment deviation. We already talked a little bit about that. That has this benefit that we are not making up this parameter, but we're actually getting an estimate, and then we have that to use in our forecast period, where we can see what the range of variation should be when we do the forecast. Another thing random effects are useful for is to introduce correlations where we might need them. This is for a model that needs tagging data, and it might be a little bit tricky to figure out correlations in a negative binomial. But in this case, we wanted to have correlations from within each release event. And in order to do that, we can set a random effect to be shared among the observations that are from the same release event, and thereby by introducing a correlation into that type of model. Another thing that's also very often problematic is if you have length observations where you would see, for instance, hole-specific length observations will very often be correlated among neighboring length groups. And in this case, we used and you might have a lot of zeros, so you can't just use a multivariate normal in some transformation. In this case, we started out with the Dirichlet multinomial, but then we took that prediction of the proportions here, transformed that with the additive logistic transformation such that it became on the scale from -infinity to +infinity, and then added this AR process, this AR correlated random variable, and then you transform it back to be proportions by the inverse. And this actually introduced that positive correlation that we might expect to see among neighboring age classes. So this thing could be one suggestion for how to deal with that correlation thing. I know that Noel has a forthcoming paper exploring similar or even more advanced solution to this thing here. So it's just meant as an example of a way that random effects can be used. And how would we otherwise take care of this? Well, there's all this ad hoc down weighting, and how much do we then need to do? Reduce the weighting to take implicit account of that correlation and all that stuff. But estimating that correlation directly would seem preferable to me, at least. Then this is more sort of a, let's say, a convenient one, nice to have, not need to have. But if you have missing observations, then it's very convenient to replace them by a random effect. And then you can program everything you program in your code, just not taking account that something could be missing. And then it will deal with that sort of by itself. And that makes it just simple and nice. Predictions, we already talked about it a little bit. Predictions are easy to make model consistent if we set things up like this. If you have a model like this, where your next state of everything you're interested in, this could be stock sizes, fishing mortalities, and let's say stock weights on some scale. And then you know how to, this is what the model has actually estimated, how to translate from the previous year to the next year and the expected noise associated with such a prediction. So when data runs out in the last year, you know exactly what to do for the next year and the next year and the next year. You don't need to come up with new rules for this. You already have everything you need from the model. And of course, I believe that this level of smoothness or noise that's in here should be something that we estimate and not something that we assign, because it's very important to determine your ability of prediction, because if you have two fluctuating process, you'll just be thrown out in some random direction. And if you have too smooth a process, indicated by the blue line here, you'll just get a biased prediction. And that's the reason that we want that to be. Then there's linking to environmental process. And this might be something that Tim will say more about, but the way that Tim has done it is very clever, because he has an underlying process of whatever environmental index that he wants to include somehow. And let's say that that's an AR process with some mean value. Then if you have missing information in that environmental index that we have observed, then this will know how to patch it. And having formulated it already as a process also allows you to predict whenever you run out of these. And that's important when we have some environmental index. So instead of putting your environmental indices directly into the prediction of, let's say, recruitment, then you fit this as part of your model, that latent process of representing the true values of that, and then you use that in your prediction. In that sense, it can predict also if this one should be missing for a year and when you need to go forward. A possible generalization of this, which I didn't learn about until recently, are these dynamic structural equation models that are described in this paper. And they are also essentially a Gaussian Markov random field that is being estimated as the underlying process. But the way that they are set up is very sort of flexible and neat. So that might be an alternative to this AR process, and maybe even sort of coupling the different processes along the way. But the take-home message is that these random variables are random effects are very efficient at setting up at including sort of environmental processes in this sense. We can also use it to link stocks by their correlation. And in this setting, we can take two already existing assessments and then link them together and defining the correlation structure that we want to impose. And then only by the correlation structure, they're sort of allowed to borrow a little bit of information from each other. If it had been observed in the historic period that when one stock go up, the other one also go up, then that can be used if you're missing observation from one stock 1 year, or even just to support the different estimations. So these were just some points where they give a really good sort of practical hand to our assessment work. Then I know Mark will ask in a second, what about lengths, Anders? Because I haven't worked much on that. But models that are based on length are, I think, always slower and always have more sort of problems converging, and especially if you only give them length data. But I think that random effects are equally useful for length-based models. I know that there are length-based extensions to WAM and NCAM, and I have an experimental one for SAM that we can look at also. In SAM, the way that it has been done is to try to keep the age dynamic intact. And so the age process might be this one, which was the same as before, and then put in a growth function, and then assume some distributions around that growth function, and then define the f at length fixed. Then I choose a number of f at length fixed point, and you can choose them so they match the f at h, but you could also choose fewer or more. And then you sort of make interpolation of the f at length in between those fixed points. I have a graph that illustrates that. So if we start by taking f at h for the different, that gives, by the growth curve, that gives rise to some length nodes. So then I define the f at length at those lengths to be the same as the f at h, because I want to be able to use both data if it's available. And then in between, you can do a spline or even something simpler if you like. And then you have f, q, m defined at every single length. And that is possible to run that part. It works fine in simulations. I haven't tested it for a real length data yet, but I'm just saying this, Mark, because I know you're going to ask, and I don't think that there's anything wrong with any conflict between random effects and lengths. So that should be possible also. So in summary, random effects it's the natural framework, I would say, and they serve so many essential roles, and not using random effects seems to lead to only unpleasant options. So if you have random effects, you can have these flexible processes for everything we care about. And the alternative might be that we have to set them constant, or we have to do some ad hoc blocking. So these 5 years will be this value, the next 20 years will be another value, and so on. We can estimate recruitment variance, and the alternative seems to be arbitrary and fixing it to some value. We can account for needed correlation, and the alternative seems to be some subjective downweighting of this likelihood component over this likelihood component. We can integrate missing observations, and the alternative is sort of to have maybe complicated code to avoid or jump around different missing observations. We can do model consistent predictions, and that avoids us having to make rules on top of our model to do the prediction. And link environmental processes. There are alternatives, of course, but they might run into problems with missing and with the prediction. And the linking stocks seems to be a very simple first step instead of having these very complex multi-species models. There are many successful implementations to look at for state space model. We have the TSA model. That's the Scottish implementation of the Icelandic model. We have Noel Cadigan's assessment model. We have WAM. We have Seattle. We have SPOC, or how we say it, SAM, and a lot of other sort of unnamed models that are based on that framework. So we don't have to figure out too much new stuff for this. Yeah, and the model is natural because it's built to optimize the prediction ability and to quantify how certain we are about it. And the only downside can be computation time to integrate over random effects, but I think we have such good tools available now that it's becoming less and less of an issue. Thank you.
Okay, thanks a lot, Anders. Does anyone want to start off with a question? I don't see any hands, so
About written ones.
Oh, there's written ones. Have to read these. So Grant, do you have a question? I can open you up if I can find you. Not from yeah, just give us a sec here. There we go. Okay, Grant, I think I've given you ability to talk. We can't hear you.
Oh, okay. Does this work now?
Now? Yep, that's good.
Yeah, I usually write a little bit better than I speak, so I'll see if I can say kind of what I'm thinking. And this is kind of with these random effects models. I wonder when we're estimating both the observation error with Dirichlet multinomials, or maybe estimating the variance of a survey that we have, and we have random effects on processes like survival. How can we diagnose whether we're correctly assigning the variance to the appropriate process, whether we have our observation model wrong, and it's, by using a multivariate normal selectivity with estimated variance, we're allowing it to be very flexible, or whether we have the underlying population model wrong, and it kind of creates a tricky problem of where there's more uncertainty.
Yeah, I think these are case by case specific maybe, but the simple answer is that we can try and do simulation studies to see if our different parts are identifiable in that sense. So make the example and see if it's assigning it to the right or the wrong place. I know that Tim has made a lot of these simulation studies, so he might weigh in here also.
Thanks.
Yeah, Dan. Oh, I'll ask Rugia to follow up first because she's got a similar question. Rugia, do you want to?
Yes. Yes. Can you hear me?
Yes, I can.
Yeah, thank you. I have a related issue. So in my model, the catchability QT follows a random walk process in time. And I define the fishing mortality as F equals Q times effort times selectivity. Would it still possible to add a process error term on F?
I think that's difficult to answer right away now, but it depends on what data you have available. But yeah, the easy answer is still that you can simulate and see if you can. But you have to be careful with confounding with this, like with anything.
Yes, I'm a little bit concerned about the potential confounding between the QT and Q catchability and F. So I'm not quite sure. I'm not sure if, as you mentioned, simulation will be helpful.
Why wouldn't it be helpful if you simulate that case and see that you can identify your parameters correctly when you change the level of the different things?
Okay, I will try. Thank you.
Dan, you had a question?
Yeah, thanks, Anders. I like you got little Mark's little cartoon shark guy in the background there too. That's a subtle plug for CKMR, but
yes.
Coming more from my background in the Bayesian world and kind of the stand ecosystem, I'm curious if you have kind of thoughts on, as we're also talking about kind of, whether or not we're looking for kind of one model to rule them all, kind of some unifying frameworks for model diagnostics and model comparison. And that's been one of the big pushes in the stand ecosystem has been kind of development, the Loo package and some of the Loo pit residual stuff, and kind of a uniform, not uniform is the word, but a consistent set of tools for kind of checking models and comparing things.
Yeah.
Wondering if you have kind of thoughts on where we are on that kind of from this ecosystem as we're potentially faced with the possibility of, okay, how do we compare, a model with these random effects in WAM to a model with these random effects in, Seattle, and these random effects in whatever other random thing we're talking about here.
Yeah. So there are definitely a few extra checks that you want to add, or at least a few different checks that you want to add for random effects models, the model diagnostics, right? The first thing is that you want to check that, let's say you're using the Laplace approximation, then you can check that one is working. And we have a good tool for that. Then you can want to check that your distribution assumptions on your random effects are good. And we have a procedure for residuals on that. And then, because things are not independent, but that's really not strictly only for random effects model, you should be very careful about which residuals that you are using for your observations, because latent process will introduce some correlation between your observations that you need to account for when you deal with the residuals. And we have tools for that built in also. And comparing across, let's say, a Bayesian model and this one, that's more tricky. Then you'll have to mainly sort of focus on prediction ability or something like these things that can be compared, even though they're completely different beasts.
Okay, thanks, Anders. So let's move on to the next presentation by Tim. Tim, you there?
Yeah, I'm here. I'm just trying to share the right thing.
Okay, yeah, we can hear you. Can you share your screen? Okay, that's good. We can see your screen in full screen mode, so go ahead.
Okay, good. All right, thanks. All right, thanks. Yeah, thanks for inviting me to give a talk. And thank you to Anders for going over all the hard stuff about random effects. I think this talk will be a little bit sort of like a breather between Anders and Noel. There's, you won't have to think so hard. Not a lot of equations. Yeah, so I was just gonna first just go over, the different types of ways we can use random effects in the Woods Hole assessment model. And I'll also just briefly talk about what the Woods Hole assessment model is, but I know a lot of people are already familiar. But and then talk about how we're using those random effects in the Northeast US for the different stock assessments that we do for age-structured assessments. And then I'll shift over to going over to some recent research, just reviewing briefly some recent research, that's, I think, helping us move towards a system of best practices for using state space or random effects models in stock assessment. There's like some published work, but there's also some work that we did through these simulation studies that Anders was referring to. And also that some of that work also, I think, will touch on what Grant's question was too. And then just I'll end with some just conclusions and some sort of lessons learned kind of things about the WAM package and what things I might do over and things like that. So WAM it's an R package available from GitHub. You can completely configure an age-structured assessment model all in R. You just have to read in all of your different data sources. There's also a web page associated with the GitHub site. It has a lot of tutorials that also come with the package for different sort of aspects of the modeling, so the different types of ways to configure different aspects of the model. There's a lot of auto-generated output once you fit a model to look at the input data, as well as all of the estimates and diagnostics that come from the fitted model. There's the packages. There's attempts. We've really tried to make it a sort of rigorous development process where we have some testing of different features when we add new features and things like that. And then just want to also mention that there's a lot of people that have worked on this. Brian Stock was the one who was instrumental in getting this into a package form and from some previous state space modeling code, and also extended it extensively to while he was here working with us. And there's also some short courses that have been given for WAM here at the center, and also up in Canada, and there's a couple more forthcoming too. So there's a lot of people that have become, I guess, interested in using it, and not just here at the Northeast. So yeah, just WAM, it's an age-structured assessment model. It can be configured to do a sort of traditional statistical catch at age model with no penalized, no random effects, no penalties on recruitment, just treating recruitments as annual recruitments as fixed effects. And then all of the transitions or these sort of survivals are deterministic, according to the sort of Baronoff-Couch equations. And then there's also, you can treat recruitment as a random effect. So it has a distributional form, a normal log normal form for the deviations. And then you can estimate that variance parameter, or autocorrelated process parameters for recruitment. And then you can also then what I would call a full state space model, where you have random effects on the survival, or what we also call parent survival, because it could be lots of things happening, but we think of it as survival primarily, but just deviations from the expected numbers at age. And then you can have this sort of different correlation structures, first order autocorrelated processes in age and time, or one or the other. And then, as Anders also mentioned, we have a lot of ability to include environmental effects. On different processes. So, environmental effects are what you would call like a specific modeling specific effects on different processes, whereas random effects are just sort of accounting for anything else that might be affecting those processes that you're not modeling explicitly. So we have ways of just modeling it on recruitment, and depending on what kind of sort of mean model you have for recruitment, so how you might predict recruitment in any given year, whether it's just a random walk, or it's just a mean recruitment model, or Beverton-Holt or Ricker. You can estimate natural mortality as an autoregressive process, or with environmental covariate effects on natural mortality. Same with catchability, and again, all of these are just sort of the effects are on like a sort of a linearized form of a transformation of particular parameters. So like whether it's the stock recruit parameters, or the natural mortality is on the log scale, but with catchability and selectivity, we don't have environmental effects on selectivity, but process error effects are on this sort of loaded space transformation for those parameters. Similarly with movement, it depends on how the movement is configured, but so you could have it as a continuous process like natural mortality, or you could have it as a sort of discrete movement probabilities, like more commonly done and when you have multi-region models. But you can have these random effects and environmental effects on the movement too. And so we use a lot of random effects in the Northeast. At least 17 stocks we treat recruitment as random effects, where we estimate as a using marginal likelihood, where we estimate the variance parameters for recruitment. For lots of we now have 4 COD stocks, or maybe 5, I think. Now there's and then also the haddock stocks and yellowtail flounder and a lot of different kinds of fish. So we have flatfish, semi-pelagic fish, as well as the regular ground fish, and then also black sea bass is probably the most complicated one, where we have a multi-region and a stock component model for that. And so parent survival, most of the stocks also include random effects on survival as well. there just a couple of them that that we haven't gone that far. And then most of the time these are set up as AR1 processes, in age and year, but sometimes we treat there's no evidence for autocorrelation in these random effects, so we just keep them as independent. We also have a lot of stocks where we have selectivity is treated as a random effect, and those are the parameters of the selectivity. So it depends, like if you have a logistic selectivity, it would be on the two parameters for the selectivity, but if you have sort of age-specific parameters, it would be on the age-specific parameters. And usually the selectivity, when I'm talking about selectivity for these with random effects, most of them are on sort of the catch with the selectivity for the fleet, but the black sea bass, we have it also on a couple of the indices for one of the regions, and I think also that's a different one, but this is a catchability. That's the catchability of one of the indices that we have a random effects for sort of an autoregressive time series process for Southern New England cod. Sorry, I don't think I didn't turn on my video. Just gonna go do that. Yeah. So then we also have some covariate effects, usually temperature related covariates affecting recruitment for two of the yellowtail flounder stocks, and also recruitment of the northern component of the black sea bass stock. And just wanted to also thank everyone in the population dynamics branch here for patience while I was trying to cobble all this information together, trying to keep all the details straight on the different random effects that people are using for the different stocks. And then just switching over to what some of the research that has been done recently. Probably a lot of people are familiar with it, but it's just going to go over some. I tried to just go over some research that honors would not be going over, and what Noel would not be going over with their talks. But just some sort of take-home sort of messages is that it looks like it's okay. It's best probably to start out with several possible sources of process error and treat those as random effects, and fit those models, and it will lead you to models that are simpler, because usually when the sources are not necessary, it'll just be degenerate. So the random effects, the residuals will be zero, and your variance parameters will go to zero. So it'll lead you to just excluding that sort of process error. And also a lot of times, even when you include these unnecessary process errors, the estimation of important assessment output, like SSB, can be robust to those incorrect, more complicated assumptions. Bias correcting is a common idea with log normal data or sort of observations, or and you might even think about it for processes like recruitment, which I think is also done for recruitment and stock synthesis. But when you treat them as a random effect, when you're treating processes as random effects, and integrating them out as and with using the Laplace approximation and so forth, it complicates things heavily and can really dramatically affect your results, particularly when the variance parameters are large. So like when you have large variation in recruitment. And so some of the simulation studies that Chen Li has led have indicated it's just advisable just to not do that. And so that's what we're doing now for most of our stocks, just not doing any sort of bias correction. And then also some other simulation work that Chen has been leading is that showing that with some multi-stock, multi-region models, that when you have sort of variability in movement over for different stocks, you can get away with more single stock model that just subsumes that variability into the apparent survival random effects. And Also, Giancarlo Correa's, he developed that growth variant of WAM, and he's done some work showing that, as you might expect, it's important to treat when you have, length-based selectivity, but you're an unusual WAM model with an age-structured WAM model. We would just be modeling selectivity as a function of age, and so it's can be important to treat that selectivity in an age-based framework as time varying when you have selectivity being a function of length. And also, more recently, Giancarlo has done some work with applying a WAM model. I just wanted, because it's the Tuna workshop, that he's done some work applying it to a big eye tuna stock in the IATTC. And then, yeah, so we have, people may not be familiar, but in the Northeast, we have this research track assessment process where we, this kind of subsumes our old benchmark process where we can make major changes in the way we model different stocks. But also we have these sort of subject specific research tracks where we tackle like just sort of topics, and we had one about state-space models, and we did a lot of simulation studies, and some of those papers have been published, but there's some of them are still in the review process, but there's a special collection in CA Fast that'll be coming out at some point soon, that I'm just waiting for all the papers to be finished, and then a collection will be more available. But from these other papers that are being worked on that are not fully out yet, we've done a lot of simulations looking at different things affecting reliability of stocks and reliability of the inferences you're making for using state-space models, and we just generally, like we were saying, convergence is, as you might expect, not going to work out too well when you have the wrong process error assumed in your model. So if you have M random effects, but you're trying to fit a selectivity random effects model, you're going to get problems probably. But also, and this goes back to traditional assessment models too, but estimating stock recruit relationships is going to be challenging. But like we did see that marginal AIC works pretty well for distinguishing the correct process error type. So we did these cross tests where we simulated and estimated models with the different sources, and AIC worked really well across the board for some certain process error types, but just generally when you have lower observation error and higher process error variability, it works really well for most of them. And then, yeah, we do, like I said, estimating the stock recruit relationship is going to be challenging. You need to have small residual variability in R, high contrast in SSB, but even when you are able to estimate it, like we did see a lot of bias in the stock recruit relationship parameters that when you fit those models. Estimating environmental effects on recruitment and M is also difficult in general, although we do have these isolated real data sets where we are able to estimate them, at least on recruitment. And then some work that Alex Hansel was leading, he was interested in different ways of dealing with these multiple surveys we have in the Northeast, maybe elsewhere, where you just have small surveys that cover small portions of the total stock area. And some, the sort of default way would be to use like a BAST or SDM-TMB to make a composite index, but you can also just include all the individual surveys and just treat selectivities as random effects too for those indices. Yeah, and just more conclusions now. Estimating the true process errors correctly is going to be challenging. You need to have good data. Again, you should just be the default expectation would be you're going to have bias in your stock recruit relationship parameters when you're trying to estimate those. And I don't know that is specific to state-space models. I think just when you're estimating in these, it's going to be challenging with the data that we have generally. And then we can distinguish these different sources of process error usually. The exact correlation structure might be more challenging to get right, but but the type of processor is we can usually distinguish that. And then we're just seeing, random effects on apparent survival, like in SAM and as possible WAM. That seems pretty often to be the best way to model the stocks that we've seen in the Northeast, not just on recruitment. And then just another thing about random effects is that where you put the random effects is going to be important for implications for reference points and how you're determining stock status. So, for instance, if you have random effects on M rather than apparent survival, that M is specific is used in defining reference points, and so it will affect your reference points. But if it's on apparent survival or the survival random effects, not necessarily. And then also the random effects, you projecting them into the future has important implications for catch advice too, and what your stock, because it's affecting what your stock is going to be in the future, and so you have to make sure that you're getting your sort of correlation process correct for those random effects when you're projecting into the future. Now, and just in hindsight, if this is something that Mark was interested in me having, is if I were to do WAM over, what would I do? I think since RTMB came into play, it seems like that would be a much better thing to use than just TMB, because you don't have to compile the code. It's easier to debug, and it's an easier programming language. R is easier than C++, and then I also wonder if we can just, if we really need to take advantage of efficiency, computational efficiency of more complicated programming languages, if we can just use AI to convert our simpler R models to those things, if we wanted to, for more production assessment work, to make things run more quickly. And then also just always keeping backward compatibility as in the back of your mind when you're extending the model, because it makes it easier for people to use existing scripts, when you've made new versions of the code, and then make things easier for everyone. And then another thing about the random effects and having where have programs, this is more of a programming thing too, that just having, when you have density dependent processes, like if you have density dependent match mortality or recruitment things, you have to do a lot of things in this sort of population loop, but things that are independent can be done separately. So like if you have random effects on environmental covariates, that's done separately. But so then when you have writing functions to do your population changing over time, you have to just have lots and lots of things that you're passing to that function when you have density dependent effects. And that's it. Thanks for having me talk. And these are just references for those papers, in case people wanted them.
Thanks, Tim. I think we've used up all your time, but we can come back to questions in the general discussion period.
Sorry about that.
Yeah. So Noel, are you there?
I am. Do you hear me?
Yeah, we can see you and hear you. Can you share your screen?
Yes.
Okay, we can see it, but it's not full screen yet.
Yeah. Make this. Yeah. Okay. Now it's okay. So thank you, Mark. So my talk will be in two parts. One, the first part, I'll just be giving some examples of how I use random effects in state space assessment models. That I think is maybe not that interesting actually. But the second part of my talk is some research I've been involved in on the statistical distribution of empirical Bayes estimates of random effects, like provided in ADMB and TMB. So how I use random effects, I'm just going to simply illustrate some uses from a recent model I developed for thorny skate. It was a kind of what I call a data moderate stock, and I don't want to go into the details too much, but I used an age-based catch-at-length model. It was done in RTMB, so it's like 36 years, 21 ages, and 110 length bins. So quite a few length bins. So we have F in this model, F random effects. So for some reason, I decided to use a separable model for F. So we have like year effects and age effects. So the age effects, I kind of treated as random effects, modeled them as a log random walk. And maybe the only different thing is that I tend to like, I just had user supplied SDs for the random walks. And I tend to like to have a higher SD for the ages where we think the process will be more dynamic. And then a lower SD at the ages for which the process should not vary that much. But unfortunately, like and then I just recently dug out the predictions of the age effects, and I don't seem to be getting that behavior in the prediction. So this is something I need to check on. But so anyway, have a random walk for the age effects. And like there's also this step here where we really constrain the age effect at a particular the effect at a particular age to be close to zero, and that's for identifiability reasons. So anyway, using them there. The year effects were just a kind of a AR1 process, so it's pretty straightforward, I think. There is a box that is affecting my ability to see what I wrote. Anyway, so here I just had a kind of a simple AR1 process for the year effects. However, if there were a few periods where there were major changes in quotas and expected, like a fishing moratoria, some of the quite a few of the stocks I've worked on, I mean, there had been periods of time when fishing was directed fishing anyway was prohibited. Then I would probably work with like basically what I call F deviations and a very few small number of main effects for fishing mortality. The kind of account for abrupt changes in wow anticipated that. Yeah. Okay. The survey cues in this model were I used random effects for those. We had like the cues were length based. We had like 110 length bins, so quite a few cues. So basically, I used a second order random walk for the younger and the smaller sizes, I should say, and then a first order random walk for the larger sizes. And this is following that kind of same philosophy. Like a first order random walk is happiest when the process is just constant, whereas a second order random walk is happy when the happiest, if you will, and when the process is linear but not necessarily constant. So this is just the RTMB code I use to achieve that. But basically, and I had to set the break point, what length did the queue process break from a second order random walk to a first order, and I did that based on kind of knowledge of the gears that were being used in the surveys for this that caught this species. But so you get kind of this behavior in log queues, and then the natural scale queues. So anyway, we don't want to get into too much of the nitty gritty here, but so that's another use of random effects. And in this one, we had M process errors. So they were 2D AR1, and we used a kind of like a plus group so that the process errors and ages 10 to 21 were all assumed to be the same. So there's this is something I like when we use deviations in a process rather than the process itself. It can make sense to aggregate the deviations, whereas it might not make sense to aggregate the process itself in some situations. But there are pros and cons to this sort of thing. And so this then just for these are the F's and N's. N's are in red, F's are in black. It's all on square root scale. Like I didn't estimate N deviations at age 0. This model starts at age 0, but the survey catches thorny scape. But I find that the process errors on M or survival process errors would be just too correlated with recruitment, so we can turn them off at that age. And also in that model, we had random effects used for the numbers at age in the first year. They were assumed to follow a stochastic steady state age distribution, and we have recruitment process errors, not just the IID errors or deviations for recruitment. So just in summary, how I use random effects. For time varying M, mostly, I mean, the stocks I work with on the northeast coast of Canada, we tend to be fairly certain that M has changed substantially, and like ecosystem scientists kind of now say that these are M-driven stocks, and F is just like usually a smaller part of the total mortality. But sometimes I use the random effects for this survival processes errors, which have a kind of a more vague meaning, I think. For this one, for this thorny scape one, I had random effects on survey Qs. But when I have length or age-based processes that I'm modeling using random effects, I tend to want to penalize them towards what I call a favored parametric model. So, for example, I usually like Qs to be asymptotic or fairly flat for as small sizes or young ages as possible. So time varying F usually to be AR1 if I have catch size comps or age comps, but for this thorny scape one, I had no sampling of the catch for size or ages, so that's why I used a separable F there. Part of the reason why I used a separable F. Again, I'd like to somehow try to penalize the age length patterns to a favored parametric model. Like if you think kind of that F or Q should basically be low for small sizes or young ages, and then increase, and then perhaps just be changed less at older ages or smaller sizes, then I kind of think that it's useful to somehow set up the random effects so that even with noisy data, you tend to get that pattern. Initial ends and random effects, but in the thorny scape example, but not always. And recruitment deviations, usually just either IID or AR1, but typically I would just fix them to be IID without, and actually fix sigma R at a large value during model building, because I would just be kind of wanting to estimate the size of each cohort almost separately during model building. But once the model is built, then you can go back and think about estimating sigma R and fitting stock recruit relationships, etc. Okay, so the second part of my talk, and it might be a bit more, possibly more informative for some, is I'm just going to describe some research I've been involved in and the distribution of empirical Bayes estimates of random effects. And the relevance of this research is to shed light on expected biases and variability when we are doing kind of simulations of state space models, and in particular, like simulation self-tests. So the first paper I'll discuss is just given at top. We just wanting to look at the frequentist delta variance approximations from mixed effects models and TNB. So the variance that TNB provides is not really the frequentist repeat sampling variance of a statistic you get by, simulating the random effects, then the data conditional on the values of the random effects. The TNB variance is actually an estimate of a type of mean square error. And I think it's okay to call the TNB standard errors as kind of prediction standard errors. But in this paper, we provided variance equations, and look, the variance, of course, will be, I shouldn't say of course, but the variance will be much larger than the TNB variance because, if you look at simulating the random effects and then the data given the random effects, it introduces a lot of variation. Anyway, we give an equation for that, but for stock assessment purposes, in this paper, we conclude that these prediction standard errors that TNB provide are usually more relevant. Like this kind of frequentist sampling variance that we developed is not really informative in the stock assessment context, but there are some situations where it would be informative. Okay, so that's that one. Next paper, we looked at what we call frequentist conditional variance, where we condition on specific values of the random effects. I mean, the random effects are unknown, but we can consider that they did have some specific values that we just don't know what those values were. And I kind of felt that this was more appropriate when the focus is on statistical inferences based on the specific values of the random effects that generated the data, which is usually the stock assessment context. So we are kind of, there was kind of one set of stock numbers or one set of Fs that were realized for a particular stock, and we want and usually in stock assessment our focus is on inferences about that specific set of stock sizes or Fs that occur. So we derived random effect. But in this conditional situation, some bias, there are kind of bias issues in the parameter estimates and empirical Bayes estimates of random effects to worry about. So we derive some, conditional bias approximations for these things, and we also derive conditional covariances and mean square errors, etc. I think an important point of this paper was that we showed that the conditional mean square error, which is what you should be using for inferences, that can be approximated with the unconditional mean square error, and that is the TNB prediction standard errors. So these prediction standard errors are more appropriate for constructing confidence intervals. And I think another important point is that the coverage properties of the confidence intervals should be interpreted as the average coverage over a range of random effects, or maybe, like, what does that mean? But the coverage could be interpreted as the average probability of containing a true value, average over, say, all years, or for example. But for any particular year, the coverage properties of like the standard confidence intervals we might create using TMB or whatever, they might not be that accurate. Okay, now another paper. So we okay.
No, we've only got a couple of minutes left, so kind of.
Oh, really?
Speed
Going
through.
that fast, huh? Okay, so in this other paper, we propose some bias correction procedures in the conditional context. And then another paper, we actually applied this stuff to look at how accurate were SAM confidence intervals, and not that accurate. Well, not bad, but I guess the SAM coverage probabilities were usually larger than 95%, but in a small number of years could be smaller than 95%. This bias correction stuff that the previous paper was about, those bias corrected confidence intervals were more reliable, but it was not straightforward to apply that stuff. And okay, I'll end up here. This is just a figure from that SAM paper showing the coverage properties, but we don't have to spend that much time on that. Thank you.
Okay, thanks, Noel. So we'll move into the discussion period now, but you can also ask Noel questions about his presentation or any of the other presentations on random effects. Does anyone want to start with a question? Okay, we have someone, just let me, so Kian, you have a question? I've given you permission to talk.
Thank you. Can you hear me well?
Yes, we can hear you.
Yeah, I have a question for Tim. I have two questions. So first question is about marginal AIC. I think you mentioned that marginal AIC worked well, but in my experience, it only works well when the models have the same number of random effects. But when they differ, AIC, I mean marginal AIC, tends to favor the model with more random effects. In this kind of situation, what would be a good way to compare the models and decide on model selection? And my second question is identifiability issues when you're estimating both like observation and process error variance. I often also encounter issues where one of those parameters tend to close to zero. So when this happens, do you have any good strategy to address this kind of problems? For example, I have been using gamma distribution as a penalty, as it often, like recommended as a default prior in Bayesian settings. But do you have any other solutions for this kind of problem?
Sorry, I was thinking about your first question more, and then I missed the beginning of your second question. But so let me the first question is, so it's about marginal AIC favoring models with, or process errors with more random effects. Is that right?
Yes. Like when you have like, multiple kind of sets of, for example, like process errors and things like that, you have more random effects. So
yeah, I didn't see, like, so in the simulation studies, like say for instance, we did some with process errors on catchability and then models was simulating process errors on, say, parent survival random effects or like natural mortality or selectivity. And so so Q would have way fewer random effects, the random effects on Q. And so when we fit models like that, and then fit models like say with numbers of age random effects to the data simulated with Q, we never got AIC picking the survival random effects models. So in fact, the survival, like there was very high accuracy for this random effects plus selectivity. Sorry, the random effects on survival. Like it didn't, when you simulated those, you hardly ever picked the other types, and when you simulated the other types, you hardly ever picked survival. So I wouldn't say. I mean, I can see why it could happen what you're talking about, but I'm not sure it doesn't seem like it's a universal or a sort of a general result that you would get AIC picking the process with more random effects. And then the second one was you had things going to zero, but I couldn't remember I missed the first part of the question.
Okay, so I can just repeat the second one.
Yeah.
So yeah, my question was about like identifiability. So when you estimate like both like observation and process error variance parameters, like I also often encounter, issues where one of them close to zero.
Yeah,
So
that's a common thing with state space models. When you don't if you have too much observation error, you'll not be able to estimate the random effects, so the process error random effects very well, generally. And we generally saw that was not done well too in the simulation studies when we had simulations with low and high observation error, and things are not nearly as good when you have higher observation error. Even and then in lots of those, and so we estimate some of the variance parameters, not all of them, but we did for like age composition data. So if you have to have good data to estimate the process errors.
no, so my experience is that even like when you use a very simple random walk model, and if you try to estimate both observation and process error variances, it often gives you, I mean, like just like what you described, if one of the components is larger than the other, one of the variance parameters, like most of the time tends to close to zero. So it's more about like inherent kind of issues with state space models.
Yeah, it is, and I think it also depends on how many different types of data like in these assessment models. It's much more complicated than like the simple state space models you'll see in the literature, where we can have several different data sources that are all informing one set of like a random latent process. And so I think that actually helps us a lot in assessment models when you have multiple data sources and you're trying to estimate latent processes. But you still need to have, if you have like multiple indices, multiple sets of age composition data or length composition data, or if that's what where your data source is.
Regia, you have a question?
Oh, yes. I also have a question for Tim. I'm very interested in incorporating covariates into stock assessment. And I have a question regarding how WOM handles covariate effects on biological processes. I'm wondering if there is any built-in mechanism to reduce type 1 error. That is like detecting a covariate effect that is not truly present. So does WOM incorporate any tools to help avoid overfitting when multiple covariates are included?
Yeah. So we did, and there's another set of simulation studies where we looked at including covariate effects, and we actually often found the opposite. So you wouldn't detect the covariate effect more often. Like you just have low power to detect the covariate effect usually. You need to have, either a combination of either a very strong effect of the covariate, very high variability, contrast in the covariate, very low residual variability in what the covariate is affecting. Those all are going to help detect the effect, but we just generally, when you account for the observation error, when you account for residual variability in the process they have the effect on, then I think that helps that issue. I think because there was one paper we did where we were fitting environmental effects on growth, and growth parameters, but when you don't allow interannual variability already, random effects in the growth parameters, and you fit the covariate effects without that, you'll get very much different inferences than if you include random random variability in the parameter, and then include the covariate effect. So it's important to account and just try to, because it goes back to just regular regression. When you include covariates, you're looking at whether it reduces the residual variation in those observations, and much like that. And this is analogous things when you have residual variation in the parameter you're having that effect on.
Okay.
So Arnie, you have a question?
Yeah, two questions. The first is somewhat elementary or fundamental. It's about, in these random effects models, we're often trying to, I guess, partition residuals or variability into observation error and process variability. And in my experience, sometimes the process variability sigma, if you like, it basically converges to zero. So the model ascribes everything to observation error. I think when I've asked some of my statistician friends, they just tell me, well, maybe your data are not very informative. And just to preempt the Tuna world, we know our data are not very informative. So are there any pragmatic solutions? Can you sort of force it to be a bit above zero, or have you any experience or advice for this particular issue?
It looks like Noel has hand up. Maybe he can respond.
Noel, do you want to answer that question?
Yeah, no, just to respond to that one, like I think it's context specific, but I find like in stocks I work with on that we have multiple surveys. Now I know that is not applicable to Tuna, but like process variability affects multiple surveys. So you get and even like in you have multiple indices. If there's process variability, like time varying something or other, then you should see that in the various indices, whereas the measurement error is just index specific. So the kind of deviations in one index will be different than the deviations in the other index. So I think part of the answer is if you have limited data, only one survey, then it's going to be more difficult to separate observation error. If you're trying to estimate both sources internally, it'll be more difficult to separate that in that situation than when you have multiple indices. But like in the Northeast US, I think it's possibly a good thing that they tend to use the survey CVs as for their for their observation errors, and but Tim is better to respond about that. Thanks.
Anders, do you want to respond to the same question?
Yeah, but it's a boring response, and but I don't think this is unique to random effects models really. If you have a model that's too complicated for your data, then something won't convert, so you get something on the boundary, and then you have to simplify the model. That's the only real solution, I think.
Okay,
I have another question, if I may.
Oh, there's a few others.
Yeah.
Okay, so Jimmy and Ellie, I noticed you had your hand up and then it went down.
Yeah, no, it was on the data quality aspect, and I think Arnie's asked it already, so thanks.
Okay, thanks. Andrea, you have a question? Are you?
Species distribution modeling in the literature, it's often talked about how when you add a spatial random effect, it confounds with the environmental effects, and the spatial random effect can absorb the signal of the covariate. And I'm wondering if something similar is happening with like temporal confounding when you have both a random effect and a covariate affecting your process.
Does anyone want to answer that question? Okay.
So,
Kyuhan, did you have a question you want to?
Mark, I thought of that.
Oh, okay. Dan, answer that.
I don't have an answer to that, but I think it does highlight a general, outside of the specific case here, right? There can be a tension sometimes between the best model for prediction and the best model for inference. And they have slightly different diagnostics, and selection criteria and stuff. And so there could be a case where you've got a model where, as you say, including these things might get you better predictions of the thing you care about, but it might kind of muddy which, the parameter of any individual estimate there. So I don't have an answer to that, but it's a common thing out, across lots of this space, right? Not just kind of in this specific space here, but there can be tension between those two objectives of really understanding that parameter and a model that makes a good prediction.
Yeah, I mean, just to add to Andrea's question is that, and this was mentioned before, basically, if you're going to include a covariate and you're going to test to see if it's important or not, you should model the random process as well. Otherwise, you will have biased hypothesis tests and more likely select the covariate than you should. And I think that's a standard statistical theory. Kuhan, did you have a question? I saw you had your hand up, but it went down again.
Yeah. I just put down because my question was more relevant to Arnie's question. So if I understand Arnie's question correctly, I think that's also about the degenerative issues in state space models. So most of my experience is actually fitting the state space models to some of the more like data kind of limited stocks. So, as I said before, I also see the problem when I use state space models with very simple like random walk. Especially like when one of the components is very large, like if process error is very large compared to observation error, I see that observation error always get close to zero. So in that kind of situation, I think it's not about the data quality. It could be something related to some more like inherent issues in state space models. So my strategy was to apply some penalties on that particular variance parameter so that it cannot be close to zero. So the gamma distribution was the one option, and it was kind of recommended in STAN forum in Bayesian setting, and it worked well in TMB as well. So I'm just curious about other people's thoughts on that.
Any of the panelists want to address that question? No. Okay. I'll add something to this. I think in these complicated models, one of the best things to do is to try and get an external estimate of the observation error from the sampling process to try and reduce the number of variance parameters you're estimating. And if you find that the variance parameter for that observation process derived from the model is much higher than from externally, that means you've probably got a misspecified model. Arnie, you had a question?
Yeah, about fishing mortalities. I'm curious about the panelists' experience and advice on how to apply random effects in the F matrix, if you like. SAM and WAM and Knowles model, you have applied it to many stocks, and you have sort of some default options. Can you maybe, highlight what the main options are, and if you may have different sort of default or recommended option that have been used for your model platform, and maybe reflect on how this might apply to Tuna stocks, where we might have length-based selectivity with almost 100 length bins. So I don't know if that is relevant. That it's a pretty big matrix. So anything about the F matrix and random effects? Yeah,
Anders.
Yeah, so there is the original paper from the Icelandic guys about that original state space model there. They had a very complicated model for fishing mortality that included several different types of process in combination. And that was implemented not by me, but by some other person in SAM. And it almost never either converge or is the best one. So the one that I normally use is just a random walk, where a correlated random walk, such that that there's an AR correlation across ages. That tend to work better than just a standard, just a constant correlation across all ages, the compound symmetry structure, and it tends to work better than the random walk, independent random walk. And these are the three options that are normally compared in SAM. But there is a fourth one, and that's that one from the original Icelandic paper. But of those four, it tends to be the one that is also the default, just the AR across ages and then random walk across time.
If I may quickly add to the question, with models like multivariate CL and stock synthesis, there is the important decision what sort of parametric shape or spline option you might use. Does any of that apply to SAM, or is it all quite sort of free?
Yeah, I mean, you might want to reduce the dimension if you have 100 or age length groups or something like that. You might want to reduce the dimension and do some interpolation in between them or something. But I would imagine that you would see a similar correlation structure across length classes that you do across age classes in that sense. Possibly even more correlation if they're closer together. But yeah. But the thing I showed in one of the last slide was an example of how you can keep sort of the dimension of your F model from your H stuff and then still do a length-based selection.
Okay, thanks. Nick, you have a question?
Yeah, thanks very much, Mark. Just a comment, and maybe it'll be a useful placeholder for tomorrow's discussion on general concepts. It was really encouraging to see Anders' use of random effects for length-based processes and also growth. Coming from the sort of archaic viewpoint of needing to consider model structure in these things, does the opportunity exist for using random effects to act as a proxy for these sorts of model structures, say extending the age structured model to account for length-based processes like growth effects, interannual variability in growth? And maybe that's a useful approach to get around the computational load associated with an age length structured model or a length structured model. Just putting that out there as a possible point of discussion. Thanks very much, Mark.
Anyone got any questions, comments? So I got a question for Anders. There's different ways of modeling the survival variation, right? You can put it on as a random effect on M. You can model the numbers as a random effect, or you can probably model survival as a random effect. So the question is, how should we do it in a general model? It seems as though Noel was suggesting always as a sort of a random effect added to the process, because then you got more flexibility. I know previously there was some computational issues with doing it that way, but maybe that's not a problem anymore. And so if we were creating a general model, which way would we do it?
I think that depends a little bit on who you ask, but I would tend, if especially if you're not too sure about your stock identification or moving in and out of the area, I would have it as just on the survival, not specifically on M, because if you put it specifically on M, then it has that interpretation that it's just M, and if you put it the other place, then it's anything sort of outside of M that could happen to the stock. I don't think there's much sort of computational difference in doing it either way.
When you say you put on S, you mean you would model N, the numbers, as a random effect?
Yeah. Tim, you have tested this more, I guess.
No, what I thought Mark was getting at was, the issue about, well, in TMB, when you have the numbers of days treated as the random effects versus the deviations.
Yeah, but you can set it up in both ways, even though you want to have it on M.
Yeah, no, but it was like computationally efficiency. Yeah. It was more efficient to do it on N versus the residuals, right?
But even if you interpret them as being M, I think you can still set up your random effects on N, can't you?
Yeah, no, I'm not talking about M. I'm talking about abundance, like the random effects. The estimated random effect is the abundance versus the residual between the expected abundance and the.
Yeah, because if you put it on the residuals, it wasn't separable or something, and
it
modeled older.
The Hessian's more dense. But I was wondering, it seemed like that and one of my bullets, I was trying to get at that because I was thinking that might also apply to other things. Like if you had density dependent effects on natural mortality in your model, you might, in that case, want the M to be and you wanted M random effects. You would treat the M as the random effect versus the residual between expected M and the M, the random true M.
Yeah, and one thing related to that is if you do program it a certain way, is it easy to turn things on and off? Like if it's treated N as the estimated parameter, if you didn't want a random effect, could you turn that off? Or is it always on? Whereas if you add a random effect to natural mortality, you can easily just turn that off, and then you've got a deterministic natural mortality process.
There might be some of the options that require a little bit more special case programming, but I think all doable in that sense. We recently did an experiment with one group from the FIMS team also looking at those efficiencies. If you had an AR process and if you have an MA process and things like how you would set it up in different ways. And if it's an AR type process, then you need to do the actual X's as your random effects. And if it's an MA type process, then you need to do the deviances for the random effects in order to get it most efficient. And so there are experiments that can be done.
Going to your question, Mark, so in WAM, you can, like as I said at the beginning, you can estimate recruitment only as a random effect and with that, so the transitions in the older ages are deterministic. And that's, I think, getting at what you're talking about. And it is more complicated to do that, but it isn't impossible. You just set the sort of things that would be random effects equal to the predicted values, and then you don't evaluate the likelihood for those random effects.
Thanks. Any other questions? Okay, it's nearly the end of the session, so I think we'll stop now. We'll take a 20-minute break, so we'll be back at 1 p.m. Thanks a lot, everybody, for the presentations and the discussions. Hi, everyone. Welcome back. So this afternoon's session is on close-kin mark recapture. And we're going to be starting off with Rich giving us a sort of a summary introduction. Rich, you there?
I am here. Can you guys hear me and see me okay?
Yep, we can hear and see you. Can you try and share your screen?
How about that? Can you see that?
Yep, full screen. That's good. Yeah.
It's coming out full screen, is it? That's
yep.
Cool.
Okay, so let's just wait a few for people to get back from their break.
Better snacks in the office.
Yeah, I should have brought some, but I've been so busy. Time to go.
We have online cookies.
Online cookies. Yeah. Okay, so let's get started. So our first presentation in close-kin mark recapture is by Rich, and he's going to give us an introduction to close-kin and its ability to integrate it into stock assessments.
Thanks, Mark, and hello to everybody, what time and wherever you are. So I'm going to give a pretty brief and mostly non-technical summary about issues around incorporating close-kin into tuner assessments, a bit of an introduction to some of the fundamentals, some medium-strength propaganda about my tuner assessments might need it. Focus a bit on the southern bluefin tuna example in terms of what long-term implementation might look like. That's probably the sort of longest term integrated example that's out there. I want to focus a bit on whether or not complex models get too difficult to integrate inside the models. And, given some of the issues around relative size of some of the different tuna populations relative to what close-kin has been implemented on so far, is there a too big, are some of those populations just too big to do it? What would the limitations be? And a bit of a talk about the current state of play with respect to wider examples. Okay, to some general requirements. I think this will probably apply to almost anything from the genetics, and really not going to be a lot of talk about genetics in this. It's going to pop up where relevant, but hopefully not more than that. You need access to an accurate genotyping method. Ideally, you want something that's going to be able to distinguish out to like second order kin. From the CKMR perspective, we're really talking about first order kin being the pair and offspring pairs, full sibling pairs, second order being half sibling pairs, animals that share a mother and a father. And one of the really important things you have to be able to do, especially as your population probably gets bigger, is to be able to calculate false positive cutoffs of the more distant kin. So You usually have relatedness statistics that'll tell you this is an unrelated pair versus a half-sibling pair. There's going to be a point at which you want to make sure that lesser related kin don't sneak into your samples. So you really need to be strict about how you can calculate those things. That's pretty much all on the genetic side. Probably of more interest to everybody on the demographic and modeling side of things. It's all about adults. That should be pretty obvious by now. Some of the basics that influence things: abundance, mortality, both natural and fishing, and age and size structure. A bit more into the advanced side of things is sexual dimorphism, in not just growth, but mortality, stock structure, and movement. For all of these different types of kin pairs, this really involves modeling probabilities that two animals that you compare are related in a specific way. And pretty much all of that stuff that you use to construct that probability is sat in your assessment model in some form or other. And the data can be integrated into an augmented stock assessment. So a lot of the basic building blocks are sat within your model. You've just got to figure out how to connect those building blocks together, construct those probabilities. Here's the propaganda sheet 101. Why would we want to do it? Well, there's a reliance mostly on longline CPUE in a lot of our assessments. There's a fairly reduced spatial footprint in a lot of these fisheries that make interpretation even harder. We're having to work harder to interpret some of the data that we've got. The composition data is often very patchy. There's probably a fairly limited return on investment in things like Persei and CPUE, though opinions may vary. I think I didn't attend the talks, but I think it was probably discussed yesterday that the realities of the, in some ways, large tagging data sets we've got don't mesh well with some of the assumptions we have to make with either the spatially aggregated models or the box model, things like mixing and so forth. And a sad reality that's probably not uncommon across all of this is investments going down, but apparently expectations are going up. We're being asked to do more and more with these models, but somehow we seem to be getting less and less to do with it. So money is tight, but expectations do not reduce. All right, let's take a really simple look at the demographic modeling for close kin. So I'm going to take a pretty simple, almost cartoon effect of this. So parent offspring pairs, so that's the first one we'll discuss. If you have an overall adult abundance, you go out there, you genotype a bunch of adults and a bunch of juveniles, and you compare all of those animals to see if they're actually parent and offspring. The chance of finding a parent, be it a mother or a father, is 2, because you've got 2 chances. You could find the mum or the dad, divided by the overall number of adults that are out there. That's pretty much almost a sort of Peterson classic mark recapture probability. So you find our number of pops, these are the recaptures basically, and you've got that classic Peterson estimate of abundance that you see there. The precision again is inversely related to the square root of the number of pops, the number of recaptures you find, but with a bonus point that CV scales with the overall sample size, not its square root. So the number of pops you find is quadratically related to that. So that's a nice bonus point. There's obviously a fair bit of detail that is missing there on things like age and size, selectivity, sexual dimorphism. But that's the general idea in a very simple setting. So moving on to half-sibling pairs, and let's keep it in a pretty simple model setting. If we have like a classic exponential growth or decay model for adult dynamics, which is given to that NT, and we have a specific fixed sex ratio given by zeta there, so we've got males and females in here, and we define the survival probability as just that exponential relationship between the sum of F and M. All right, so consider that we're comparing 2 juveniles born in different years, in years T2 and T1, and we have that difference in the birth years. So the probability that they are a half-sibling pair is really defined by 2 bits there. You've got the fact that you've got to survive, the mother or the father has to survive in between the birth of the first animal and the second one. So that's the numerator on both of those terms there in that first equation, and the denominator is just that probability basically that particular male or female could have been the parent in the year of birth of the younger animal. And if you've got a 50-50 sex ratio, you get that magic formula for the half-sibling pairs, which is 4 times the cumulative survival divided by the number of adults in that younger birth year. So that sort of compares, you can see you're more likely to get for certain survival traits, more half-sibling pairs than pops. All right, that's the simple case. I used to think reality wasn't a cartoon, but you might do, fun politics might suggest that's not the case. But in our reality, some, perhaps not all, of the following are going to matter. So reproductive success changes with age or length, right? Fecundity increases, maturity increases with age or length. You're going to get more likely per capita to be a successful parent. Sexual dimorphism, you've got differences between males and females in terms of both growth and mortality. And then you can layer onto that any spatial or stock structure that's in there. Some populations are more accommodating than others. We'll talk a bit about that later, but most of the general tools that you're going to need are either in or are modifiable or addable to the assessment structure. So a lot of the basic building blocks are in there. You just have to know how to put them all together to construct those probabilities. So Southern Bluefin Tuna case study. This is probably the longest term of all of the examples. It's a project that's been around for almost 2 decades now. The sampling is relatively simple. So we have sampling of juveniles in the Great Australian Bight, which is that orange ellipse just below the Australian North Island. I can say that from Tasmania. And then we have adults sampled on the unique spawning ground, which is just off the southern tip of Java, which is that blue ellipse. That juveniles at age 3 is an important point. It means that at least for that case, we can be pretty sure that we can get the juveniles that relate to the single adult spawning ground, and we can get them at an age that we pretty much know. We don't have to deal with the fact that we're not entirely sure when the juveniles were born. That's an important factor for model simplification. So it utilizes both pair and offspring pairs and half-sibling pairs. As of this year, pretty much, we've got 119 pair and offspring pairs and around 157 cross cohorts or different birth year half-sibling pairs. So it's built up into a pretty informative database at this point. The pair and offspring pairs were integrated into the assessment in 2014, so they've been in there for some time. And then the half-sibling pairs were integrated 3 years later. So they've been in there for almost 4 or 5 assessment cycles all told. And in 2019, both those data sets were integrated into the CCSBT management procedure. So for SBT, it's fully embedded into the assessment, has been for a while, and it's also built into how the management of the stock is done via the management procedure. So it's a central long-term monitoring data set. What is it about the SBT example that made it went well? There's been 2 major genetics platforms being used. Firstly, it was microsatellites, later on single nucleotide polymorphisms, but there was a lot of work done to do the genetics right and make sure it's consistently right. If that's wrong, everything that follows is going to be wrong. So getting that right is really important. Not as exciting as all the modeling, but consistent engagement with the RFMO, your members in the RFMO, the policy people and the stakeholders is a massive part of ensuring you've got the sampling good, ensuring you've got buy-in. It's not the most exciting bit of the process, but it's massively important. Focused sampling, I think, is a really big one for this case. It really helps reduce model complexity in this case. Just going quickly back to the fact that we can get those juveniles at age 3, and we're pretty darn sure they're age 3, and that we can get adults on the spawning ground, so not off the spawning ground, not at spawning time, where we have to deal with the fact that, well, we've sampled it over here. What's the probability it could have actually been up on the spawning ground? We're sampling animals on the spawning ground, so that makes it simple. Accommodating life history. I suspect this will be the exception of the rule, but the sex ratio has been consistently sort of 50-50 from the pops and the half-sibs. So there doesn't seem to be a major difference within the age or size-related relative reproductive success of the animals. And they don't show the sort of systematic lifetime long or short dynamics where you got animals that are consistently, their growth trajectory is consistently above the mean length at age or below. I think Mark's going to talk a bit more about that and how you have to deal with that from a half-sibling pair. So we didn't know this at the time, but they ended up being a pretty accommodating species. The answer it gave was more optimistic. Don't doubt the importance of that when you're trying to get buy-in to a method. Again, we're pretty lucky in that terms, but that was a feature in terms of getting buy-in. But I think ultimately what it's done is proven itself to be a really cost-effective long-term monitoring program. That's not a factor of luck. All of the work that went into it did that. And I think its demonstration as that sort of key long-term monitoring data set is is pretty much accepted across the RFMO itself, even with the funding issues that are always there. Okay, does it start to get too complicated to integrate to a model? Are you better off doing it outside? I would say no. At least for the SBT case, we're migrating everything across to RTMB, which I think Darcy's going to talk about tomorrow. But all up, that's about 150 lines of code. That's pretty comparable to the mark recapture likelihood that we've got, and I think that's true for most mark recapture likelihoods, even if it's spatially aggregated, that's honest about what you don't know at release in terms of you don't really know the age at release. So I think it's comparable to the stuff that we already use. And the data sets aren't massive either. You group all of these comparisons, even if there's hundreds of millions of comparisons, into workable covariate bunches. So it's not a massive data set. It certainly doesn't hold back the model in terms of runtime. How about the more complicated stuff? Well, the sexual dimorphism, it's not something that doesn't really move the needle for SBT, but I suspect that's just not going to be the case for almost anything else. What about aging error and the fact you got length-only samples? So we have a mix with the SBT, and when you only have the adult length, you've got to integrate across that, but that could be more systematic in other examples. And we don't have spatial stock structure. So I'm just going to briefly explore that issue with Indian Ocean yellowfin. This was a design study, so not what we call the full wet study where you get all the samples, but you put the models together and you look at sampling strategies and you ask, okay, given a bunch of objectives about what you want us to achieve with this project, what design strategies work and how many samples do we need? So the yellowfin, the Indian Ocean, is a bit more complicated. So I want to use that one to address the how big is too big in terms of model complexity. Okay, for the Indian Ocean yellowfin setup, it's certainly in the assessment at the moment, it's set up as a 4-region model. That's that graphic just below, with recruitment sourced internally. So whatever the spawning stock is, I mean, this is a rough approximation to probably what really goes on, which is, I guess, more of a separation by distance issue. But for the purposes of this work, we said, okay, each area has its own spawning stock and the recruits are sourced internally. So, if you've got a bunch of adults in, say, region 2, in a given spawning period, in a given quarter, they can't really be the parents of anything in region 4 that were born in region 4 because they're not there. A really important, again, and this leads to the sort of focused sampling issue, is that we assume you can get juveniles between the ages of 0 and 1, so at most 1-year-old from the purse seine fishery. Why do we do that? Well, because we can reasonably assume, or we hope we can, that they wouldn't have moved. If they're going to move as well as the adults that can move around, that really does blow out a lot of the complexity within the model. So we focused on the case where we're going to focus on getting the youngest animals possible from that purse seine fishery to ensure that at least the juveniles, they aren't going to move. The sub-adults and the adults, we assume we can get from the mix of the far end of the free school selectivity from the long line and the deeper hangline fisheries. Yellowfin in the Indian Ocean showed clear sexual dimorphism in both growth and maturity. There's been genetic aging work for yellowfin, so we assume that we'll have access to that, but there's an aging error associated with that. We're estimating in the model, we've got reproductive output, we've got adult movement and adult natural mortality, so we're trying to push it about as far as we can. And the question was couched in the terms of, okay, what are the overall sample sizes and also a split between juveniles and adults? And how precise will be the key assessment quantities that we're likely to get out of that? For the spatial version of the pair and offspring pairs, I'm not going to go into too much detail. I think Mark will probably pick up some of this, and I'm just giving a summary, so I'm going to keep it pretty light on the equations. The probability looks pretty similar to the non-spatial case, but you've got a back-in-time element for the adults. What do I mean by that? So say we sampled a bunch of juveniles in region 4, and we're going to compare them to a bunch of adults that we sampled at some time later on in region 3. So the adult itself was not in the region that those juveniles were born in, but we want to figure out, okay, we sampled it some years after the juvenile was born. What's the probability that given we actually sampled the adult in region 3, that it was actually back in time at a younger age in region 4? So it's a bit of a backward sort of way to look at it. But that's the additional complexity that goes in there for the spatial point. Added to which we've got aging error for the adults. For the spatial half-sibling pairs, again, the equation, apart from dealing with the spatial bit, looks pretty similar. But you've got to account for the fact that, if he had, let's go back to the thing, we're trying to figure out we got a juvenile born in region 1 a few years before, comparing it to another juvenile born in region 4 some years later. We've got to figure out that, okay, we think that the putative parent was in region 1 when the first one was born. What's the probability that it survived and it moved to region 4 when the second juvenile was born? It's probably a little cleaner, I think, than the pot probability. It doesn't have this sort of back in time thing. But in terms of keeping the model efficient, it actually helps to use almost a hidden Markov model type construction for how you model the survival and movement of the adults for those two cases. So if you think about it as a state, you're interested in the state where an adult has both moved and survived between two places, or from the backward part of it in the spatial pops, that you knew it was alive in this particular point sometime back in time. Where was it in relation to the birth of the juvenile we're comparing it to? But using that HMM type construction for that dynamic makes it pretty clean in terms of their program. What were the objectives that we're being asked to look at? Explore the CVs and the adult M, the overall depletion, the stock status, and mean recruitment. All right, so this is a bit busy, but this sort of links into what kind of numbers are you thinking for big tuna? Yellowfin's pretty big, so I don't think it's as big as WCPFC in the Pacific, but it's pretty big. And what we came up with, we've got four measures there. In the top left, we've got the CV on mean recruitment. We've got top right CV on adult M. The bottom depletion in the total reproductive output. That's the SSBs as proxy for that. This is the real thing. And then the CV in total reproductive output. On the y-axis, we've got the overall number of samples each year, and we assumed a 5-year sampling program. And on the x-axis, we've got the proportion of those samples that were juveniles. So we can focus that sampling towards juveniles or adults. It's going to change the mix of half-sibling pairs and pops. And in general, what looked like the sweet spot to get stuff that was reasonably accurate would have been 30,000 samples per year, and a more biased split towards the juvenile, so 70-30 split. So if you sort of look at where that sweet spot is, it's in that sort of lower down on the y-axis and a bit further to the right on the x-axis. Would that overwhelm an assessment model? Well, I would say again, no. The TMB code that we did to put together the design model is about 175 lines of code. So again, I don't think it's any more complex than a realistic spatial tagging model would be. What about the data sets when you get into this? Again, even though we're talking about bigger populations, we're talking bigger numbers. Again, you're grouping everything into these useful covariate bunches. So I don't think it'd be much bigger at all than the current SB data set. And that does not shut down the assessment whatsoever. So I don't think it's a real limitation, even as you build in, a reasonable amount of complexity and reality, and you're getting bigger data sets in terms of overall comparisons. The big population problem, it's not just about costs. I mean, yes, if you've got a bigger stock, that means you've got more costs. You've got to sample more animals, you've got to genotype more animals. But once you have that platform sort of set up and given them the rate at which genetic costs keep coming down, I think that's the more manageable cost. Probably the more expensive bit is the sampling platform, how you actually get those samples. That can be expensive, and actually processing it in terms of analyst time. But just genotyping the samples, I don't see that as the bottleneck. Just to give a bit of context on cost, for the last, I guess, 10 years, it's been in long-term sampling mode for the SBT case, and that sampling cost is it's less than $1 million by a fair bit. It's less than 0.1% of the overall fish reward value. And I wouldn't expect that for long-term projects that have gone through the initial startup phase, got everything developed, and you're just in collecting that data as a long-term monitoring, I don't think that number is going to change too much. So it's not a massive blowout value, I wouldn't think, subject to all of the whims and variances of current investment in science and the RFMOs, but it's not a big blowout number, I don't think. I think the bigger issue is the number of comparisons you have to do when that population gets bigger. You want your data set to be informative, all other things being equal. If you've got an order of magnitude higher population, you're going to have to really ramp up your sampling to get the same sort of numbers of informative pairs. I think there's a fair bit of work that you can do to deal with that. I mean, one immutable thing is that false positive threshold. It has to be maintained, right? You don't want less akin pairs creeping into your data set. because that's going to bias things and make a mess of it. Be smart about what you compare, especially when you're talking about the half sibling pairs. If I think about skipjack, you had two groups of juveniles that are born 4 or 5 years apart. It's pretty unlikely that any of the parents would have survived between the birth of the first group of animals and the second. So in reality, they're probably dead comparisons. So don't do them. The key bit is that if you compare everything to everything else, that's going to make you have to work a lot harder with your false positive threshold. You're going to wind up throwing away more samples. So be smart about how you do that. I think one of the issues that I think Mark might talk about this with the Western Atlantic, but we're starting to have this with SBT, is to structure your comparisons by groups. So if you got all your juveniles and you compare everything to everything else, you'll have to have a pretty strict false positive threshold that's just for one for all of the comparisons. If you group those into animals that were born in these two cohorts, and you do a bit more work on the front end to figure out, okay, we have false positive thresholds and false negative probabilities for groupings, you'll probably wind up throwing away a lot less data and be more efficient. Definitely don't go cheap on the number and quality of the genetic markers. That's the stuff that's going to make the discrimination of unrelated or lesser related animals from the ones you want. So don't go cheap on that. And certainly at the moment, there's a lot of tools out there in terms of whole genome sequencing and kin finding tools that can really make the most of the fact that the level of genetics that we can get to now can be really, really powerful in being able to discriminate between different kin pairs. So you can make the most of it on the genetic side. But I think that's one of the bigger issues. It's not just the cost for the big populations. I think it's just the fact that you got to do something with the fact you're doing hundreds, perhaps even thousands, billions of comparisons as you go along. So how's the CKMR tuna rollout going? Obviously, SBT is pretty well established. I think Western Atlantic bluefin is done, and I think the Eastern Atlantic bluefin tuna design work is done. I think Mark's going to talk to these, and I think did I see Carmen online as well? Pacific bluefin tuna, I think the kin finding is done. The papers are out there. I don't know the status of the CKMR modeling. I don't know if we've got any Japanese colleagues that know a bit more about that. South Pacific albacore, the initial kin finding process has been successful. And in the next couple of years, the model development will be going to look at the initial modeling and to look to integrating that into the assessment. As far as I know, there's nothing concrete for yellowfin or big eye at the moment. There's on design work, but hopefully they're the next stocks off the ramp. I would expect skipjack to be challenging for all the reasons we said, but again, never say never. Technology rolls on, and so does the genetics. So maybe that's going to be something that's a little further down the line. This is our gene tagging program. I'm not in any of these pictures. I don't do cool stuff like this, so I like to live vicariously through some of my colleagues because I don't have cool pictures. But this is our gene tagging program at the Great Australian Bight. And thanks for your time, and happy to take any questions now and later on.
Thanks, Rich. I've got a little bit of time for a question. Anyone got a question? Okay, we have one here. Jim. Jimmy Yanelling, can you ask your question? Can't hear you, Jim. Someone else has a question.
How about now?
Oh, you can hear you now, yeah.
Oh, sorry. I forgot my question already, but awesome graphics. And
I wish I was in it.
I think there's pictures of you with a whale shark. So not buying your never get to do anything for things.
One time.
But I do, yeah. So with just for the Indian Ocean, the region ones, where was one of the cases where you had a spawning adult in one region and the juvenile was there, and then that same adult moved to another region and spawned, or was sampled? I guess, is that a difference that needs to be distinguished?
That's a good point, Jim. So yeah, I mean, I guess from the half sibling point of that is that the sampling would have had to occurred after the second animal was born, right? It's lethal sampling, so it's not going anywhere, right? So there is an assumption that you sampled it at some point back in time. further back in time from when you sampled it, it could have been the parent of two animals that you're comparing, and you got to figure out if that both, it was, conditional on the fact that it would have been alive. And in the region where the first animal was spawned, then some years later, you got to figure out what's the probability that it both survived and moved to the area that the second animal was born in. But yeah, it'll always be sampled after that fact because it had to, once it's sampled, that's that. Well, the adult's not sampled. In the half-sibling pairs case, you don't see the adult at all, right? So that really only, I guess that only really applies to the pop case. But similar sort of thing though. You're trying to figure out, you sampled that adult in a given year, you're actually trying to figure out, okay, I sampled it over here, it's a lethal sample, it's dead, but I'm going to compare it to a juvenile that was born some years before, and I want to figure out, was it back there? What was the probability that, given I sampled it here in this place, that it was back there when that juvenile was born? That's that one.
Eric, you have a question?
Yeah. Can you guys hear me?
Yeah.
Oh, fantastic. Hey, Rich. Thanks
Hey,
a lot.
Eric.
Yeah, a couple questions or comments. So you were talking about the case in, say, Skipjack, where you had two candidate half siblings that are 5 years apart, and it's very unlikely that they would be, that the parent would have survived that long anyways. So you could effectively kind of toss them out off the top. And that's sort of an example of using the population model to actually inform a sort of prior on what the kinship probabilities are. And I've always kind of thought, there is that information in the model. It does seem like one could do it sort of jointly, so you didn't have to have hard thresholds for things, and actually include or exclude things. But I think we've probably talked about this before.
Yeah, that's true. But I think it's a good point. Trying to get it clean is certainly so. I know that's where the SBT case, and I think, I won't speak for Mark, you'll probably have some views on this, but I think getting into those more distant kin, I don't know what you think about that, Eric, but I think it's going to get harder and harder to be able to be that clean if we really want to use some of those more distant kin that some of the whole genome sequence is getting. We can probably do it for the populations we've got now for the second order, but I suspect those demographic priors and a willingness to, probabilistically model the fact that we don't know for sure it's exactly this kin type, but it could be these ones, might be something that we might have to move to include some of those more distant kin and the information that they've got. I'd be interested to see what you think about it.
Yeah, no, yeah, well, that's an interesting question. I mean, I think it becomes really difficult when it's not just half siblings, because the unobserved ancestors, then you don't know sort of what ages they were or what sexes they were or when they existed. And it becomes, and whether they were in the same cohort or not. So it sort of becomes something where the effective size starts to drive the probabilities of finding these more distant kin. But I think it could be very helpful for looking at connectivity issues within the same thing. And then the other question I had was just sampling juveniles that are, potentially young of the year within some of those boxes. Is there any concern? I mean, how spatially clustered within the boxes is the spawning effort of the species, of the stocks stuff? Is there any concern that they're not well mixed yet? Or
I think so.
Probably take account of that with your sampling spatially?
I think in reality, it's a pretty, the box is a pretty simplistic way of divvying this up, but certainly from the population genetics from that region and things, that there's probably much more spatial stuff going on at lower scales, and that separation by distance is a bit of an issue. So this is a pretty rough carve up of, at least, okay, if you have to deal with some of the sort of spatial separation issues, this is a pretty simplistic one, but I suspect there's a lot more going on in reality at finer scales, is what you're alluding to. That really, I guess some of this lays onto the issue with the tagging models and how deep, how much beyond the box model do we really have to go to model some of this stuff. And I think some of the realistic separation by distance issues are similar, that we'll have to get down to a much finer gradation of spatial scale to deal with it properly. But this is about as simple as I could deal with.
Yeah, cool.
Okay, thanks, Rich. Let's move on to the next presentation and keep any of your questions for the discussion section at the end. So, Mark, can you hear us? Can you? share your screen. So Mark, we can't hear you or see your screen. Are you there? Having a slight issue with the connection here.
Quick question, will we wait?
Yeah, sure.
So, Rich, did I hear you correctly that it was significant and important that 3-year-old juveniles are sampled, or is the age of the sampled fish not that important?
I think for the SBT case, the 3-year-old is just that's one where by targeting a very limited length range, you can be pretty much certain you're going to get 3-year-olds. And so it's not important that they're 3. You know, it could be 1, they could be 2, they could be 5. If you can nail them at 3 in this particular case or any given age, you don't have to integrate across the fact that you actually didn't really know the age of the juvenile that well. I mean, you can do, but again, you start to get some smearing going on. So this general thing about focused sampling is like, if you can't do it, then you can't do it. You're probably still, but it's something that further down the track in the model you'll have to deal with. That uncertainty in the juvenile. In the adults, it's non-negotiable, right? You just don't know, especially if it's length sampling, you don't know how old they are. I see Mark on there, but yeah, the 3 wasn't important, just that you can nail a single age class. That was the key bit. I'll shut up for a bit now.
Okay, Mark, can you I think you were a participant rather than the panelist, so you should be able to talk now and share your screen.
That's a relation test facility insurance, right? So I guess we'll pass the trend estimate for different tissue samples, population sizes, bit weights, and all that stuff. What sample sizes, CVs that
You were using ours.
No, it's a stand model.
Hey, Mark, are you there?
This is a stand CK.
We can't hear you.
It's amazing.
Okay, we seem to have a technical issue. Nick, are you there? Maybe we should do Nick's presentation first, and then hopefully we can sort Mark out after that. Yeah, thanks, Nick.
Yeah, I can go ahead. Can you see my slides?
Yeah, it's not in full. It is full screen now. Yeah, it's good. So go ahead.
Okay, sweet. Thanks. Okay, so I'm Nick. Just briefly, I used to be at the National Marine Fisheries Service working with Atlantic tunas. I was only there very briefly, but I mentioned that because that's where my understanding of the tuna world comes from, or lack thereof. I'm now at the Pacific Biological Station on Vancouver Island for DFO. Okay, so we've been in the paradigm of developing these integrated stock assessments for quite some time now. I would argue that fisheries management has been all the better for it. Now, the models are I'm referring to sort of our data-rich age and size structure assessments here, and they're quite flexible by nature, but the reality is they're often really fit to 3 different types of data sources, right? Our age, our size structure, our information on removals, and indices of abundance, whether from fisheries or surveys. Now, with the advent of close kin theory and its uptick in application and interest, I've been sort of wondering whether we shouldn't routinely collect genetic information to integrate into our assessments according to close kin. So to that end, this sort of framework I was thinking about was, what if every time we were sampling an otolith, we took a tissue sample as well? So theoretically, this wouldn't increase the marginal cost of taking the sample. I suppose you'd have to store it. But the real cost is in the processing of our genetic information. And so thinking, well, how would that look like integrated within an assessment and sort of our classical age structured stock assessments? And also, how much information would that actually provide, and in what form would it show up in our assessment? So I wrote this little paper looking at that. So I looked at 3 different life histories that importantly differ in the size of the spawning stock. So we have a cod-like population, a flatfish-like population, a sardine-like population. So cod, at the end of the time series, is around 200 million spawners, flatfish around 50,000, and sardine around 5 million. And so I looked at, with respect to close skin, how many years you collect close kin, and also the annual sample size level you're collecting. So simulated parent offspring pairs, half sibling pairs, grandparent grandchild pairs with aging error. Now recall, this is a situation where you're sampling from the catch at age. So the assessment was privy to 4 different data sources. I should mention it was a 75-year fishing time series and an informative 2-way trip. So you have information on total removals for each year in the time series with a very small standard deviation. So they're basically treated as though they're almost known. Age composition sparsely collected for the first half of the time series and in every year for the last 25 years with a multinomial sample size of 100. An abundance index with an uncertainty of standard deviation of 0.5 for every year in the time series. And then close kin samples for the terminal 5, 10, or 20 years in your time series with sample sizes of either 100, 1,000, or 5,000 collected in each year. So this is how I imagine the data might look like given to an assessment. So you have the sample year of your firstborn, the sample year of your secondborn, the age of your firstborn, the age of your secondborn, the number of comparisons with those similar covariates from which all your close kin calculations can be made in combination with output from your population model. And then the number of successes, so the number of POPs found and half sibling pairs and grandparent grandchild pairs found. Now, for context, this is a snapshot. This data set actually contains about 10,000 rows, and it's from one of the moderate sampling cases, 1,000 every 10 years. Okay, so what you're looking at here, top row is the cod population, middle flatfish, bottom sardine. In our columns are the annual sample size levels, so 100, 1,000, 5,000, and then within those panels, the number of years you collect it. And this is the number of pairs we find across simulations. So you can see at the 100 sample size level, we're basically not finding any pairs. We're starting to find pairs in the flatfish model. We're getting almost to 100 total pairs found. For the 1,000 level, we're still not finding pairs. For cod, we're starting to find pairs in the thousands for flatfish. Recall, that's the smallest spawning stock. Even at the 5-year level, we're in the thousands of pairs. And then sardine, we're finally starting to find pairs just below at 100 total after 20 years. Okay, so for the 5,000 level, we're finally starting to find some pairs for cod. Recall, this was the highest spawning stock. We're at just below 100 after 20 years. We're finding a ton of pairs for flatfish. And we're starting to get up into the thousands for sardine, at least at the 10-year level. Okay, so what does that mean in terms of information content given to a sort of classical assessment? So here you're looking at the standard error of spawning biomass in each year of the time series for an assessment fit with close skin integrated, over that for an assessment without close skin integrated, and 1 minus that value. So as you go higher on the y-axis here, your spawning biomass estimates are more precise, and we'll call this percentage improvement precision. Okay, so for the first column, at the 100 sample size level in each year, we're basically not giving in any information to the assessment. Recall, we weren't really finding any pairs at that level. At the 1,000 level, we're still not providing any information really to cod. We're starting to provide quite a bit for the flatfish case, and you can see it slightly increases as the length of collection increases there. In sardine, we're finally starting to uptick in the amount of information we're actually providing the assessment. At the 5,000 level, we're just starting to give information to the cod case. Remember, it was only really starting to find pairs at that the highest sampling scenario, so 5,000 for 20 years. Flatfish, what I noticed here is that the peak is no longer increasing, suggesting we might be saturating the amount of information we're getting. And sardine, we're finally starting to give the assessment quite a bit of information, around 60% improvement in precision there. So this is a good reminder that the information is sort of backdated, right? Because you have to go back to the year of spawning of the individual. And that's why these peaks are 5 to 7 years prior to the terminal year of the assessment. That's going to correspond, at least in this case, to the mean age of fish you're catching, given we're sampling from the catch at age. Okay, so more pairs equals more information. Not exactly a revolutionary finding. I don't really expect the Nobel for this one, although there's a chance they got it lost in the mail, perhaps. But what does it mean when we look at the percentage improvement in precision as a function of those pairs found? So at the top row, we have our cod case here. You can see we were never really getting above that 100 level of pairs found. And we're at basically a 20% improvement or below. And for the other life histories, I've had this inset here that zooms in on the 0 to 100 level. You can see that finding is somewhat persistent, that we're basically at 20% or below improvement when you're finding less than 100 pairs. And for the flatfish model, you can see we've sort of way oversampling here, as we're getting not as much information out of additional pairs found. And for the sardine case, at around 1,000 pairs found, we're improving the model at about 60% or less. And if I zoom into the flatfish model at that 1,000 level, we're getting about that same level of 60% or less improvement. Okay, so that's the correctly specified case. Now, what often keeps me up at night is different obvious ways in which our observation models can be wrong. And one aspect that I've come from the doing my degrees in academia to the real world messy assessments is we're often much more uncertain about removals than maybe we lead on or assume in our assessments, particularly removals during the early time series. Exclusive economic zones were declared in 1980. We might not have had as much information coming from our fisheries prior to then, at least on the domestic side. So here you're looking at what if, well, the true catch is double that we assume in the first half of the time series, and what results from a relative error in spawning biomass perspective and a relative error on fish recruitment and natural mortality. So we're overestimating on fish recruitment, overestimating natural mortality, and that's the resulting pattern and bias for spawning biomass. Now, can close-skin help us right the ship here? Recall that we weren't really finding any pairs in the cod case, so it doesn't really make a difference. We're finding a ton of pairs in the flatfish case, nearly completely helps us right the ship in the second half of the time series. Similarly, for sardine, it helps us right the ship in the second half of the time series. Now, recall we're spitting catch almost as though it's known, so we're still misspecified those removals early on in the time series. So we're still getting that quite a bit wrong. So a more flexible approach to fitting catch here might be warranted. This is sort of the power a bit of the integrated approach here, is you're a little bit more robust to any major bias in one data set. Or a purist might say it might help you more go back and evaluate the impacts different data sets are having on different aspects of your model, to be able to, in this case, hopefully go, well, maybe I should allow for a more flexible fitting catch in the early time series, review my assumption there. So tuna specific opportunities, in the sense of, do we need close kin for tuna? Probably don't need to tell you guys this, you're already collecting it quite a bit, but I've posted the exclusive economic zone I work in, top right there. And when I zoom out, what you find is that it's really such a small slice of the North Pacific. And long story short, I'm charged with assessing groundfish stocks, and it seems pretty unlikely that we're not receiving recruitment subsidies and giving them north and south. So collecting it in my region without a massive international effort maybe doesn't make the most sense, but you guys are already set up to work internationally cross borders, and oftentimes, in the Atlantic case, set up to assess populations on an ocean-wide scale, which is pretty neat. Uncertainty in catches, I have to assume you're also reasonably uncertain in catches, maybe also in the recent time series, given IIU fishing and the nature of monitoring high seas fisheries, but maybe not. What I recall from the tuna world is there are no few surveys, pretty reliant on fishery CPUEs, and I posted this at the bottom right here. There's a reminder that these close skin data can basically give you sort of information on spawning biomass over a wide range of years, especially when you continue collecting them. Maybe allow you to, it's basically an absolute abundance index, and you might be able to forego relying on those fishery CPUEs. So obvious ways our observation model can be wrong for tunas. I think about these top two catches and catch per unit effort, each of which close skin can help you. Okay, so more on the practical side. As Rich mentioned, it does get quite computationally intense. A little bit of an aside on this. I originally submitted this paper with POPs and half-sibling pairs. The reviewer said, well, really to make it more realistic, you should add in GGPs and aging error. I said, oh yeah, great idea. And I did. The model immediately crashed with this error. I believe it's a memory overload error. Anyway, I spent a long time trying to make the model more efficient to get it to fit. But eventually I gave up and I had to switch from mixed effects, specifying recruitment as random effects, to penalize maximum likelihood, and was able to get everything to fit. But that was the sort of compromise I had to make. Just a reminder on why it gets so computationally intense. Not only is this table huge, but with aging error, for each one of these rows, you go in here, you have a coded age 8. You got to say, well, what if that's a true age 7? Run your calculation. What if that's a true age 6? Rerun your calculation. And so you had 20 ages, you've got 20 times 20. 400 calculations for each one of these, additional calculations for each one of these rows. And it has around 10,000 rows. That being said, on computational intensity, it sounded like Rich had some ideas about how to collapse these down and maybe not make as many comparisons. I think it's more of a problem to be overcome than a problem not to do it or not to integrate it. And I say that mostly on account of being probably at the lower tier end of fisheries biologists when it comes to programming ability. So I have to imagine folks would find efficiencies where I failed. Or you can make the compromise and go to penalize maximum likelihood. Okay, so some more lessons learned on my end. Definitely do sex specific, although I can't remember if most tuna assessments are sex specific or not after you're getting sex specific compositions. But I got too far along in this project before I realized, oh darn, should have definitely done it sex specific. But it will make it more computationally intense. There may be some fun aspects to consider with respect to the expected reproductive output of males compared to other males of different sizes and ages. Bring in size. Again, this should help with fecundity if you think fecundity is more a function of size than it is age. Although, again, this is going to be more computationally intense. You have to find the size at the year of spawning. So basically taking growth transition matrix backwards, which sounds like fun. A couple tips on computational intensity. As one might seem obvious, consider aging error probabilities below some low number to be 0, such that you're omitting quite a few of those calculations, basically rounding your aging and precision matrix. Conditioning on the second born for GGPs, certainly. And for half-sibling pairs, there's some plus group considerations there, but you may be able to do it in many cases and have a switch that if you're getting into the plus group to use the survival term. Anyway, that gets a little bit into the weeds. With that, I'll open it up. I'd like to acknowledge some folks that gave some tips along the way: Eric Anderson, Paul Kahn, Mackenzie Mazur, Robin Thompson, 2 anonymous reviewers, funding agencies, NOAA and DFO. And yeah, I think the elephant in the room is our tuna population is too big. I think you're probably definitely closer to that cod case. So you're gonna need quite a few samples. The other elephant in the room is aging and aging error. I don't recall many ages in the tuna world, but anyway, I'll stop there.
Okay, thanks, Nick. Does anyone have any questions?
Maybe a quick question about life history. Is it important whether an individual fish has lots of offspring or if it's a species that has few offspring?
That's a great question. Relative to others?
Yeah, I mean, for example, cod is famous for having an immense amount of eggs, whereas a shark has very few offspring.
Yeah, I'll have to turn to Mark or Rich. Would you think that would make much of an effect? Mark, there he is.
That scales the total.
Yeah, this is a chance for me to test my audio. Can you hear me?
Yes, we can. Yeah.
Okay. Yeah. No, it doesn't matter fundamentally, because the point is that everybody still has 2 parents. that doesn't change regardless of how many siblings you might have in the same litter. So the key point is that everybody has a mother and a father, and that's what you test in close kin. It's only ever telling you about the adults, really, the adult stock, not the juveniles. So it doesn't fundamentally change things whether you're a cod or a grey nurse shark that has a litter size of 2.
What about half siblings?
Well, we only do half sibling comparisons. They're only meaningful across cohorts, not within the same cohort. So part of what could be said about the point Eric raised with, young of the year and so on, we don't do comparisons within the same cohort because that creates all sorts of other unwelcome awkwardnesses. So across cohorts, it's still the case that, the chance that basically your mother is the same as the mother of that other one born a couple of years later is just as Rich said. I will say a little bit about larval sampling later if you want me to, but yeah, it doesn't mess it up.
Can I quickly add one thing there?
Sure.
I think it doesn't mess things up, but it does change the basic sample size question. If you assume there's a relationship between the critters with tons and tons of offspring have bigger total population size, then the amount of samples you're going to need to get the kins that you need will change, right? But it doesn't change the fundamental equation inside there, right? So conditional on population size, it doesn't matter.
Yeah.
But you change the population size because with different life history, then that does change the how many samples are you going to need to get enough kinship.
It does, but it's really the adult population size here that's the meaningful one. So yeah.
So just to follow up on that, I'm not sure if this is, but if you're having live births or whatever, like a shark does, it's more likely that the juveniles are going to survive. Does that spread the juveniles out among lots more adults? Whereas, like if you're a tuna and you spawn 1 billion eggs, but they all pretty much die, and it's you have a lower number of proportion of adults that are successfully having juveniles or something like that.
No, don't think about it that way around because it leads to confusion. The way to think about it is always that every sample that you get had a mother and a father. There's lots of other potential samples that you didn't get. They might have been dead or you just didn't collect them. But every sample you had one mother and one father. And if you think about it that way round, the fog of confusion will dissipate a little bit.
I agree with that, Mark. But could I just pop in with one other thing? I mean, I think, Mark, like hearkening back to your humungodon examples long ago, right? If you have something like a shark that only produces a handful of offspring, I mean, then basically your model becomes much less sensitive to age or length based variation in expected relative reproductive output, right?
Yeah.
So in a sense, you could possibly have a simpler model, right? You know that all adults basically are going to be pumping out the same number of potential juveniles.
Yeah, you are 100% right. And there's a difference between, you can get away with simpler models for for mammals, things that behave like mammals and basically have a fixed number of offspring. Some sharks are like that. For fish, including tuna, you have to worry about this size fecundity link. And so in a sense, you need a more complicated model. So you've got a few more options with some shark and mammal species than you do with fish. Yeah.
Okay, I think we should move on with Mark's presentation before we have any additional questions. David, keep your question for later through the discussion period.
Okay, so how's that looking?
That's great, yeah.
Okay, pity I can't actually see it. It's a good thing that my audio was off earlier when I was complaining about Zoom because there were things I was saying there that probably didn't want to share with the group. Anyway, this gives me the advantage that I can. Thanks, Nick, for jumping in there, and it makes it a little easier for me actually because I know what the other two presenters have said. So thanks for asking me along to this. Okay, so I don't need to do too much recapping of close kin, I think. I'm going to list a few examples I'm not going to go very technical. I will hit one or two of the big questions that Mark was dangling around, and then perhaps I'll spend a little bit of time talking about spatial stuff at the end, leading into the discussion. You know what it is. The data you need is tissue samples from a small proportion of catches of the catch. We can get into that later. And what we do is pairwise genetic comparisons between all our samples, or most of them, to look for these two types of kin. Because everybody, when you were born, you tagged your mother and you tagged your father. So from a point of view of putting it into models, it's helpful to think about the covariates of each sample that are going to influence probability. And so the word to remember, it's not a word, but is SILACs. These are the things that can potentially matter, will affect the probability that you find kin. Sex, year, or quarter, it doesn't matter, of sampling. Length and age, these might be measured with error. And in some cases, you need to worry about where you collected the sample, its location. These don't all matter in all situations, but those are the big five. So from a data point of view, you're doing pairwise comparisons between fish, each of which has potentially 5 covariates. You could be dealing with 10-dimensional arrays. In practice, you often only need to worry about 7 or 8 of those dimensions. The other things don't matter depending on what job you're expecting that fish to do, to be an offspring or whatever. And then you need a list of pairs, which pairs are pops and half siblings. And there'll be hundreds of those, but not typically thousands. So one thing where I kind of disagree with Nick is on the computational burden. Even if you have things like length and age error, it's really not too bad to compute the probabilities for these big arrays. But there are a number of tricks that one needs to do to get things reasonably efficient. And as Rich said, the close kin model computes probabilities for finding kin pairs for each of these combinations of comparisons. The outputs, I don't need to say hardly anything about this because Rich has already covered it. The point to make here is it's the underlying population dynamics model is the same pretty much as in assessments, and it estimates the same things that are in assessments and sits very naturally, as Nick has described, within the framework of a standard assessment. In fact, you can't generally pre-organize your close kin data to just plug it in as an index to a model because it's going to involve the same parameters as a model would anyway, and you just can't do it. There's also diagnostics of goodness of fit, which someone can ask about later. The benefits, you kind of know, it's sort of like a supercharged version of tagging in some ways. Robust to all sorts of things that conventional fisheries data is not robust to. For instance, selectivity doesn't even feature in close kin equations if you typically set things up right. You don't have to sample everywhere. Unlike that's what you should do with things like CPUEs or surveys. And you get straight to absolute abundance. You don't need to put scientists on boats to tag things. You can just sample from the catch. And if you don't like the precision you're getting, just spend more money and get more samples. Yeah, okay. I'm putting up a quick table of some fisheries examples that I've had some involvement or awareness with. This isn't a comprehensive list. The reason I'm doing it is, oh yes, I will just say wet or dry studies, as Rich said, some of these studies have come through to completion and giving an answer with actual data. Some are just at the stage of design studies and may forever remain as design studies because it is crucial with close kin to plan the hell out of what you're going to do in terms of sample collection before you start to avoid getting an inadequate data set at the end of it. The reason really for the table is to illustrate that there's a lot of different quirks that have to be faced in these situations that have required adapting the code in particular cases. What do you do if you've got larval samples? That's what has been forced to be the case for Atlantic bluefin tuna. Well, that creates a particularly whole problem because the larvae are going to be they're coming out of the same litter. So you can deal with it, but you have to make some modifications which are unpleasant. Aging error is a situation in many cases, but not all. SBT kind of remains the paradigm case of the perfect close kin species in terms of easiness. But we've had to deal with aging error in other situations, and you can sort of do it. Lots of quirks. Don't try and build one overarching model that can accommodate all of these situations in the same piece of code is my advice. Go to the situation you're dealing with, pick out the quirks that you need to deal with there and just deal with it. But since you're talking about developing next-gen software, it would be a bit foolish perhaps not to build close kin into it, since it's already part of the deal for 3 tuna species and more are likely to be added to this disk. So suitability for close kin, it's always a function not just of the life history of the species, but also what you can sample about it. If you can do amazing sampling, you can deal with a lot of life history cases, but tuna generally are really good. And the key thing is they have many spawning chances after reaching adulthood. The most limiting factor for close kin is often species that only get to spawn once or twice, then that doesn't really work. Tuna also move around a lot. That's good. It's harder for species that have got really tight local spatial structure. Basically, there's nothing weird about tuna. They have a high unit value and they're abundant, which I see as a positive. We'll get onto that in a minute. Many people see it as a negative, but I don't. And with tuna, the usual fishery data are particularly problematic, CPUE, as we've heard. Limiting for some populations will be an unwillingness or an inability to sample certain key life stages. If you can't get the biggest adults, you're probably in a fair degree of trouble. And you do want some youngish, knownish age animals to be your potential offspring and potential half siblings. So if you can't get those, it can be problematic. But that's a sort of population specific thing. Generally, tuna are really good. Are they is it going to be too expensive or too abundant? Well, I think this popped up a little bit, maybe it didn't, in the previous talks. For close kin, the sample size you're going to need to get a certain number of kin pairs, say low hundreds, and that's what determines your precision. It scales with the square root of the adult population. The cost of getting a sample is a fixed thing. If you're getting it for $20 US, you're probably paying too much, getting all the sampling and genetics. If you're getting it for 10, please let me know your phone number, because I'd like to know. But the point is sample size scales with square root of abundance. The catch scales with absolute abundance. Things like turnover tend to cancel out in these equations. So roughly speaking, the tax rate of close kin scales inversely with a square root of the population size. And it's also a lower tax rate for species with high unit value. So bigger is better value. Nevertheless, I wouldn't start with skipjack. It's just too daunting. Start with something where you only need 150,000 samples like yellowfin. Doing the genetics isn't really a problem. Big genetics companies can handle 1 million samples if necessary. Eric Anderson has been involved with programs in the US that have handled several 100,000, what are they, salmonids. And as to cost, you don't have to put any scientists at sea. So that's good stuff. The other context is world tuna fisheries are worth about 40 billion a year, apparently. They're being run largely off CPUE, which is pretty unreliable stuff for tuna. It's worth having good information. And as Rich said, the ongoing cost of southern bluefin tuna close kin is currently, I think it's something like 0.03% of fishery value. So I think those pictures kind of speak for themselves, but I'll let them speak to you for a few seconds. Here I sort of go off script a little bit. What's the limitation on uptake? I mean, it's actually quite a cheap technique and it's a good fit for tuna. I think one problem is that close kin will continue to be perceived as luxury science as long as scientific committees keep agreeing assessments, no matter how many caveats they put on it, as long as the assessment comes out despite data getting worse and worse and worse, it doesn't kick the system into action to do anything about it. Caveats don't really make stuff happen. And the second point, well, I will certainly get a few people offside on this one. I am pro management procedures and management strategy evaluation based on data. However, quite often what can happen with management procedures is that some years are spent building a beautiful castle of a management procedure based on, in a situation, in an RFMO, where there's fairly limited data about what's gone wrong in the past, for instance, catch misreporting and so on. So you test it against scenarios, but with a kind of committee designed version of what a wolf might look like. And this is not actually a wolf, really. It's a grumpy purple hamster downloaded from the internet. So inevitably, what happens is this turns up. You've got exceptional circumstances. It's not good, painful. So that's not actually the punchline. The punchline is this. Everything works a lot more smoothly if you build your management procedure and test it based on good data. And with a slightly revisionist take on history, this is sort of what happened at CCSBT. It had two goes. First of all, it built a management procedure based on horrendously shonky classical data. The wolf turned up and it all fell down. Then CCSBT got hold of some really good solid data, part of which was close kin, but that's certainly not all of it. The second time around, it was much more easy, painless, well, not painless, but cleaner to build the management procedure. And the wolf turned out not to be so scary and hasn't been back since. There's a lot of political capital invested in developing management procedures and getting them on side. It takes about the same time as a close kin project. And I do find myself thinking that it kind of makes difficult to get close kin and things onto the table. So, you know, maybe focus first on getting some solid abundance data now that there's a tool that can do it. I will slightly skip over the point here, but I will say that these projects that have happened largely because people are desperate. They're not starting from the situation of we've got an assessment and we'd like to make it slightly better. They've arisen because you know, it's been impossible to suspend disbelief any longer. Clearly, things are quite bad, and they've been so bad that people have been willing to have a go at close kin. So, yep. Right, we have to move on. Software needs, well, we've already heard a bit about that. It's really the same population dynamics that you'd like to put into an assessment anyway. I would say it's got to be age and it's got to have sex structure in it to do it properly. And it should be capable of taking account of length because length and age both affect close kin probabilities and individual growth does matter. And if you ignore that, you get an appreciable bias in the models. To go full length and age, which I think Andre is going to talk about tomorrow, is really complicated. I suspect we could do close kin that way, but it is horribly complicated. So do you really need to do it? The only modification I'm aware of is a slight modification to the plus group, too boring to go into here, but it's not difficult. And you should build in any case, some provision for aging error, because I do think in future epigenetic age is going to come through for tuners, and you'll need to deal with it. Other than that, there's nothing fundamental in the software platform that needs to change, but there are a number of coding tricks for close kin itself in order to, you know, for instance, make it run in reasonable time. And it would be quite interesting to get together and have a sort of focused meeting on what tricks you need to do to get the thing to actually work. This has already been done in the full sense that I describe here. Sort of, I have a SBT version from years ago, but it's been done recently for Halibut. And there's a version that Anders Nielsen and I cooked up this summer for SAM, all done in RTMB. And they do all this, and the runtime is fine. So it can be done. As long as you don't go too mad with spatial. So spatial, first of all, it's often irrelevant to close kin. If there's only one spawning ground, it doesn't really matter when you do the sampling. So slightly different to what Rich said. It's by accident that we have adult SBTs from the spawning ground. But I actually think it would be fine if we caught them wherever. We all know they're coming back to the same place to spawn, and that's where the tagging happened. So yeah, they might go all over the ocean, but you can still get away with a non-spatial model in many cases. If not, there's hardly any equations in here. This is what a standard close-kin model without space looks like. I've just used Z to describe the sort of 4 important covariates of a sample emitting location. And the probability that animal I and J will turn out to be a parent-offspring pair, you need to think about what animal I's fecundity would have been back in time when animal J is born. So that's where you're interested in, like back projecting size and things like that. And then you also need to compare that against all the competition that might also have been J's mother or father, which is the total fecundity at the time that J was born, which comes from your population dynamics. If you need to make it spatial, the only adaptation conceptually you need to do is to think about not just when J was born, but also where J was born. And since if you're not measuring J when they're very young, as they were in Rich's yellowfin or in the Atlantic bluefin examples, then J may have moved. So you need to do some projections, hidden Markov models and things are involved here. But conceptually, this is not a particularly difficult modification. You can make it hard. Spatial close-kin, I think Matt in the first talk yesterday brought up several different types of spatial pattern there can be. Onto genetics. So Pacific bluefin start spawning in one place when they're young and small, and as they get bigger, they move to spawning in different places, quite different. Discrete, faithful, and heritable. This may possibly describe what goes on in Mediterranean Eastern bluefin tuna. I'll come to that in a second. And then we have the musical chairs model of spawning, as I call it, which is more or less what Rich described for yellowfin in the Indian Ocean. You swim around a bit, the music stops, everybody has a bit of a spawn, you carry on swimming, might end up somewhere else, the music stops again, you have another spawn, and you drift around, but without any particular plan to it all, just waiting for the moonlit night and the opportunity. There may be more. These have different implications for how you would set up a spatial close-kin model if you had to. And the limit here is really Eastern Atlantic bluefin tuna. So there's a fairly incredible piece of work, largely by Carmen Fernandez, looking at design options for how could you sample to do a close-kin model for Eastern bluefin tuna. The thing about them is there's 3 sort of largely discrete, perhaps more, even spawning sites in the Mediterranean. We don't know whether adults return to the one spawning site, keep going back there, whether they move around. We also don't know if they do stick to one spawning site, if it's the same one that they were spawned at. So these 2 different types of behaviors, whether it's faithful and whether it's heritable, they have different implications for close-kin models if you collect samples in different places. So this piece of work, in order to figure out the most efficient sampling design, looked at 5 possible fleets that samples might be obtained from, 4 of which are in the Mediterranean, and the 5th is the Atlantic generally. I've cut out the boring bit of the Atlantic in the middle. I hope I haven't done away with Iceland in the process, Arnie. So 5 different fleets to consider. It turns out that if you were to sample all of them and build a very complicated model, you could learn about whether things are faithful and heritable. You could figure out the underlying biology. But it's a hell of a model. It's the outer limits of human complexity. I think only Carmen could actually have, I honestly can't think of anybody else who could have worked through this and got all the modeling details to work. So an alternative is to give up on trying to understand the detailed structure in there. Just get your samples from one place where you believe that the fishery is well enough organized to do it, which in this case would be larvae from the Balearics. It's actually a cervi. And then get your other samples from out in the Atlantic when the adults all come out here. So the adults all mix here outside of the spawning season. It's only during spawning where we face the issues within the Mediterranean. and keep a non-spatial framework. We won't learn as much, but everything's much simpler. It's not an obvious choice. But the big lesson behind this is control your sampling carefully. Focused sampling is what made SBT tractable, and it's the same for other situations. I won't say anything much about this now, but it would be a lot of fun to explore the musical chairs sporting model in the context of what Jim Thorson was talking about yesterday. There's a lot of information to do with relative distances and times that's buried in the data sets here. Whether you need to do it is another question. Would be fun, but we may not need to go down that route. And to be honest, we don't know in practice what you're going to find spatially with in a lot of close-kin settings. So what has tended to happen from a pragmatic point of view is to design the close-kin sampling under the assumption of a non-spatial model, that everything is well mixed in some crude sense, or perhaps a simple spatial model like Rich and Laura's yellowfin in the Indian Ocean. But make sure that the sampling is spread out enough in space that eventually you'll be able to diagnose any, as it were, incomplete mixing spatially. You could ask about that in the questions if you like, and be prepared to change the model if you encounter that. The spread the sampling means you can generally diagnose whether anything funny has gone on. Eventually, close-kin data will reveal even quite complicated spatial patterns, as in the Atlantic bluefin stuff, if you are willing to wait long enough. But in the meantime, simple enough may still get you answers that are useful. Again, we turn back to the question of what's good enough for management, and a bit of simulation testing here is the way to go. I don't think spatial stuff is going to be that bad, but let's just move on to the final slide before Mark gets too twitchy. So close-kin, it really fits naturally on top of standard population dynamics. There's a few tricks, but nothing you need to basically change. For goodness sake, don't try and build a next-gen framework that can account for every behavior that is seen in tuna and other fisheries that might affect close-kin. Keep it to the cases that you want to concentrate on and be prepared to modify it. I think it is worth putting a simple close-kin mark recapture straight away into the development of whatever you come up with, partly because it's really good practice to get past some of the little complications and tricks that you do need to deal with. That business about half siblings and false negatives and stuff, Rich, if you can get your car to start this week, I've got some ideas about that. We could actually meet up. I think we can do a little bit better there. But it's worth putting simple close-kin into something just to get used to it, even if it's non-spatial or it's a really simple spatial one that you don't really think will work for every situation. Expect to have to change it later. You won't get everything right because close-kin data itself reveals so much about breeding biology that is really hard to anticipate. But also to think about how spatial you really need your answers to be. Didn't get a very clear answer on that yesterday when I kind of asked after one of the talks. It may often be easier and cheaper to control the way you do your sampling and limit the ambition of questions you try and answer than to try and build the all singing, all dancing model that can cope with every kind of sampling that might be available. And with that, that's it. So thank you.
Okay, thanks, Mark. Open it up to questions on any of the presentations or just the topic in general. We have Eric, you have a question?
Yeah, just a question for, I guess, Mark. So yeah, I mean, I definitely appreciate the advice to don't try to build an Uber model. You know, for people that think about software and abstraction, it always seems like, oh, shouldn't there be a way to do something that would apply to everything? But I was just going to say, I mean, it seems that what would be valuable potentially would be a sort of generic kinship probability calculator that would basically take the underlying latent variable that I'm assuming is in most stock assessments, which is just sort of stock and location specific abundance and fecundity, age specific abundance, and then turn those essentially into kinship probabilities. It seems like that would provide a really nice sort of simple drop-in mechanism for people to calculate kinship probabilities. Any thoughts on that, Mark?
Sort of, yes. I mean, when I'm talking about putting a simple close kin into the next gen, that is really the kind of thing I have in mind. I mean, I teach I've taught a close kin workshop a few times and gone through the exercise with some of the participants of building in the entirely age-structured version, which is quite standard code. It's not that difficult to extend it to a version with length in it as well. It's more than I could teach in a close kin course, but that is almost now boilerplate code that we have for halibut and for the SAM thing that Anders Nielsen and I did earlier this year. So that kind of stuff can go in. But if you go spatial, you have to take account of things moving around or not moving around enough. And so that's why I think you can't really build in a perfect all singing, all dancing spatial version in round one. But you can get most of the other features in as boilerplate code, and I think it would be highly worth doing. Yes.
Yeah, I mean, it seemed to me that like possibly an R package that used RTMB with sort of a shared variable, which was a big matrix of abundances and ages and lengths.
Well, I wouldn't make it an R package. I think I think the real value comes from people actually working through the 100 lines of code or whatever it takes, and then building it into whatever situation they're dealing with. But I think it's very valuable to have clear examples of that code lying around that people can use and modify. I actually really dislike the idea of going packagey here. And I'm encouraged that I think a lot of what Mark and Arnie are talking about is having the flexibility to be modular and plug things in and tweak them according to specific cases. But absolutely, some of that stuff should exist. It'd be great to have a nice workshop somewhere and spend a week putting this together and seeing what it would look like.
Yeah, I guess part of what I've been thinking of too is for calculating the more distant kin pair type stuff as well. Like if you wanted to go back 5 to 10 generations or something crazy.
I think that does take us into a different ballpark.
Totally, yeah. It's not particularly useful for abundance estimation, but I think for other things like connectivity and such, it might be more valuable.
Yeah, so just to follow up, Mark, on the spatial stuff. So if we decided we wanted spatial models for other reasons, for management, or like we had traditional tagging data and we needed it in there or something like that, are you able to put a basic close kin mark recapture in there that would work with a basic spatial model, or are you saying that's too complicated?
I don't think it's possible to answer that in a general sense. I think it depends, but the model that Rich described for Indian Ocean yellowfin, or a little extension of that allows juveniles to move perhaps as well, you could put that in. But my general feeling about close kin and about spatial close kin is that you can't really go that generic. Like the eastern bluefin situation is very, very different. The Pacific bluefin situation is different again. So sort of yes and no. I think once you've seen what the code looks like for something like that Indian Ocean yellowfin, then you can make an informed decision for specific cases you want to consider. I think it is conceivable that you have a spatial model underneath it, which is more complicated than the spatial representation used in close kin, and that you can ignore some of the spatial complexity in your that's within the assessment, within the close kin probabilities in some cases. In other situations, eastern bluefin being one, the thought of having to split up the catch within the Mediterranean into different sort of natal homing things is horrendous. I don't know, Rich had anything to offer there?
Thanks, Mark. David, you had a question?
Yes, thanks, and thanks, Mark, for the presentation. I was wondering, I know that Rich mentioned that the sampling is done on a modified ratio where you sample more juveniles in the SBT case than adults, and I assume that's because of the relative size of those two populations you're sampling. And I was wondering whether, Nick, when you did this simulation analysis, which was very nice and showed how impactful closed can be for different life histories, whether you consider different splits or were they always considering that you are sampling 50-50 juveniles and adults. And I think that would be a relevant thing to understand how you should do that, because obviously, we're going to look for sampling designs that are going to be efficiently in cost-wide in terms of cost as well.
Yeah, I was sampling in direct proportion to the catch at age, but Mark and Andre's paper looked at specifically weighted sampling of that catch at age, I believe.
Okay, Lisa, you had a question?
Yes, can you hear me?
Yeah.
Okay, perfect. Thanks. Thanks for all the talks. They were very interesting. I'm interested in, once you have a functioning closed-kin model, whether it's integrated in your assessment or it's a standalone model, you essentially have, your assessment saying, this is my absolute biomass, and then you have an alternative reality with your CKMR data. What tools and what diagnostics have you found particularly useful to kind of convince yourself, which sources of data are more accurate or giving you a better result? Because I'm sure, CKMR ideally would give you a better result, but obviously we've talked about all the possible biases. So I'm curious if you have some great diagnostics that show, obvious red flags with CKMR, or alternatively, if there's still a lot of work to be done in that area.
I'm not sure who's supposed to speak at this point. I think probably Rich. But I mean, well, so I'll try and be brief. First, to David's point, yes, it matters a great deal which which fish you choose to sample for efficiency. This is actually the problem that halibut is going to hit. You want to sample youngish ones and big old ones ideally, and you can dramatically change the efficiency and precision and cost of what you're doing according to what you take. When it comes to diagnostics, close-kin there's a sort of simple general way of doing diagnostics, which is to calculate the observed and expected number of kin pairs for different combinations of covariates. So for instance, you could be looking at whether you've got as many close kin pairs across a wide distance where they're widely separated as you expected. The models pretty much always get the totals right. So that there's quite a straightforward way of assembling diagnostics. But I think it would be quite useful to hear from Rich on that consistency type thing, consistency checking.
Yeah, I mean, from the certainly for the SBT to the video, and everything's not working. There we go. Yeah, we do a lot of diagnostics. Mark said to look at.
Hey, Rich, we're not hearing you very well. Yeah, we still can't hear you. It's cutting out. Okay, so I'll mute Rich. So John, you have a question while we wait for Rich to sort himself out?
Yeah, thank you all. Thank you, Mark, Rich, and Nick for the talks, and Eric for all of the additional insight. My question kind of relates to scope of inference. So half-sibling pairs and parent-offspring pairs technically estimate slightly different quantities, don't they? Because infertile adults are invisible to half-sibling CKMR, but parent-offspring CKMR includes those because the adults are directly sampled. Is my understanding of this correct? And if so, how do you deal with that slight discrepancy, or is it something you generally ignore?
Well, the first comment there, I think, is that the probabilities are fundamentally different. It's not. Rich showed obviously a simple example where you just have n on the denominator, but in fact it's a fecundity weighted version of n that really appears there, and half siblings. Yeah, I mean, they definitely look different. And you get situations where, like, there will be more half siblings if the reproduction is concentrated onto fewer adults for the same amount of total offspring output. So, as a rule, you pick it up. There's a quite logical way to pick it up in the close kin probabilities that reflects fecundity at size. And this is one of the reasons you need to be a bit careful with it. And so you don't really have a tension between the two because you calculate the probabilities in a way that's logically consistent with sort of fecundity things. You do generally make the assumption that there aren't non-breeders in the population. Like if you're a 180 centimeter SBT, it's not that you decide not to breed or not. You're the same as all other 180 centimeters SBT. Having said that, there can be situations where you're worried that the half-sibling kind of absolute abundance component is a bit biased, because this is generally to do with patchy sampling of half-siblings. So it is a real issue in the Atlantic bluefins, where we know that the juvenile sources would not be sort of well mixed. And in that case, you can decide to turn off the pure abundance signal within the model and just rely on the POPs for the total abundance signal. And you kind of bulletproof yourself against some of those considerations. Over.
So, Mark, just to follow up on that, for the half-sibling issue of underestimation, is it affected by unsuccessful breeders?
No.
Or is it, it's not?
No, you have to be a persistently unsuccessful breeder. We understand, and the model is perfectly fine with some years you get lucky and some years you don't. But you have to have a situation where some animals are like perpetually infertile despite their size for it to go wrong.
Well,
so
not necessarily.
Pardon?
Yeah, not necessarily unfertile, just unsuccessful.
Well, whatever. Yeah, that's right. So that's a bit biologically odd. So for sharks, for a number of the shark applications, we've been forced to rely on half-sibs only. And the reason we've kind of got away with it is because adult fecundity is deemed to be fairly well understood. Often there's no relation to body size, or if there is, it's sort of mild and understood. Doesn't work for all sharks. But yes, we are making the bet there that there's nothing, that it's not the case that some sharks are perpetually successful and others are not. this kind of thing becomes much more dubious in terrestrial applications where an animal might, occupy a really good breeding territory and continue to pump out offspring. Less of an issue in the sea, and we tend to think that. I mean, Jim Thorson thinks that fish are particles, right? So we don't worry too much about these differences.
But just to follow up on this, the unsuccessful breeder thing makes sense. What about if you never sampled a sibling from that breeder? Is that the same thing? Because you never saw anything that was produced by that breeder, so there's no signal at all about that breeder.
As the questioner asked, if there are fish that perpetually never contribute to the juveniles that you're sampling, they are invisible.
Yeah. So if you had a population,
it's not. But sorry, just to clarify on that, it has to be not just due to a random event. It has to be some persistent property of that adult.
Yeah.
Yeah. But even just randomly sampling individuals, some adults will never have their offspring sampled.
That's okay.
Yeah.
And if you don't have any other information, is that a problem?
The way I like to think about this, because there have been times when I've thought, wait, the fish that aren't producing any offspring, they're going to be, do we have to account for that in some way? If you think about any particular cell in your population, which is given by the year and the age and possibly the length, the CKMR essentially depends on the assumption that all individuals within that cell are exchangeable. And individuals can still be exchangeable even if random things happen to them, right? But they aren't exchangeable if they're skip spawning, for example, right? So if you got, half your sharks in that cell spawned last year, so they're not going to spawn this year. So that has to be dealt with. But if it's just sort of a thing, like if you roll the dice for half of the, or for the fish in there and half of them, you say, okay, they're not going to spawn this year just randomly. They still are exchangeable, right? It's kind of like, it's sort of like a finite De Finetti's theorem thing right there, right? So if you basically have, how am I trying to describe this? But basically, if the individuals in that cell are a random mixture from some mixing distribution, they're still exchangeable, right? That's maybe not a particularly helpful way of trying to explain it. But
I think the skip spawning example is a helpful one there, though.
But I mean, yeah, I actually this sort of started. I started thinking about this last summer when I was trying to reformulate CKMR, because the sort of traditional formulation is ratios of expected values. You can find edge cases where that sort of breaks down, and I think that the key is kind of exchangeability in the little subgroups of the population that you're basically calling the individuals that have the same expected relative reproductive output.
I think that's true, but I think with tuna, we're not in an edge case situation anyway.
No. I mean, you're never in an edge case. I mean, the edge case situation's in a ridiculously contrived case, right? Like completely stupid case. But it did sort of bring up this kind of like, oh, actually thinking about it in terms of exchangeability makes it easier for me to think about what are the processes that we have to worry about or not in terms of, and if it is just randomly some individuals some years don't reproduce, but if that's totally random so that everyone in there is still exchangeable, then it's not as much of a problem as if it's associated with covariates, or if it's, like you're saying, persistent across years or not independent from what happened the year before.
Maybe we can have a bigger discussion on that offline. But let's see. David, do you have a question?
Yeah, a completely different topic is about some of the comments that Mark made about the lack of buyout on closed skin by many of the tuna FMOs. And I think for that reason alone, I think it'd be worthwhile having integrated closed skin in an assessment model. I think the experience, my experience at least, has been that as models have, assessment models have allowed a broader set of data to be incorporated to the assessment, you've had increased buyout from those scientists that were particularly interested or that have the ability to collect some of these other data sources. So I think that alone would help. And, currently this seems to be a barrier. It seems to be like a completely different method that is not merged within the assessment, and probably generally because of ignorance. So I think that alone would be a really powerful argument to incorporate some sort of closed skin, even if it is not fully spatial, into the new assessment model. Thank you.
Rebecca, you have a question?
Yeah, hi. I have a question for Mark. Full sibling pairs are not used very often, and it looked, based on a table you showed, that they have been used for school sharks. So I'm wondering, what is it about that situation that makes full sibling pairs either useful or feasible for them?
Oh yeah. Yeah, so well, it makes them unavoidable. The thing about full siblings generally is that for most species, it would require two animals to mate in different years. So unless animals are pair bonding or have really tight spatial structure, that doesn't happen. So they're very, very rare across cohort and can be ignored. For the school shark, they have quite large litter sizes, and there's not that much multiple paternity. So within any one cohort, you tend to get, one litter tends to have a lot of full sibs in it. Perhaps because of quirks of the sampling, and because there's quite a bit of skips, there's the skip spawners. We do have a lot of full siblings in our samples. So we might as well use them. And they're not from the same, sorry, they're all from the same cohort. But the real complication with the full siblings actually is that if full siblings are abundant among the adults, and there will be a number with school shark, then they generate what I call full thyatic pairs, things like aunt-nephew. They're going to be quite common, or somewhat prevalent in the population, and genetically they look like half siblings and grandparent grandchild. So they're a sort of potential contaminant of the second order kin that we're looking at. So we make use of them because the full siblings per cohort does contain some information, but mainly because we can't avoid thinking about them in the context of second order kin. Just to illustrate the kind of weirdness that can come up in close kin that you shouldn't try and build into the Uber model of everything, because it normally won't matter. Over.
Thanks, Mark.
Arnie, you have a question?
Yeah, it's related to what David described as an integrated model that includes CKMR, and he also mentioned data sources. My question is, because we know that for albacore, for example, we will have CKMR data, but we also know that for skipjack we will not. Do you guys think that it will be practical to use the same software for those assessments, so you can disable the CKMR part, or would you think it would be separate software? A related question, I guess, is for southern blue tuna model, can you disable the CKMR and see what the model does without it?
Over to Rich.
Mark?
Okay. Well, I mean, I'm not a fan of building. This is just a personal thing. I'm not really a fan of building huge models and then turning large parts of them off. I tend to feel it makes sense in any one specific situation. I mean, you don't have to build hundreds of these models anyway, so you've got time, especially with these projects. Closed-skin takes 4 years or something, so you have time to develop the model you want. I don't know enough about. I mean, there's no conceptual problem with turning off a likelihood component associated with closed-skin. So you could write code that's got it in and then turn it off. But I am mindful of something like SS3, which is, well, it's horrendous. There's 20,000 lines of code in there with bits and pieces for everything. And I worry a little bit that some of the edge cases might also intersect. So the one that I have in mind in particular is if you've got sort of spatially varying growth, that's going to get quite tricky. The code you could write for a non-spatially varying growth case is really not that bad with closed-skin. Like a couple of hundred lines will get you there. Once you've got that other stuff in, it's going to get a bit horrendous, hard to maintain, and so on and so forth. So I tend to favor writing the one you need for the application you've got. Having said that, I have run models with closed-skin sort of turned semi-on and semi-off. I think SBT might fall over without it, but I'm not too sure. It does provide, I will say that closed-skin should provide something you can treat as a proper likelihood. So it shouldn't be something that you kind of tiddle around with down weighting it. It's either in and you trust it, or you've decided for some reason it's rubbish and you chuck it out. Yeah, not sure.
So Mark, following up on that, can you explain why we need length in the closed-skin mark recapture? Is it just
yes,
length is related to fecundity, or is it something else?
It's primarily that. The one thing is that selectivity in the situations I've thought about, you reckon it's length based, and so that when in a situation where you only have the length of a sample, as long as the selectivity is only affecting length, so that age is, as it were, unselective within length, then it makes it quite easy to set up the mechanics of summing across the unknown ages that the animal might have been. It actually just makes it easier. If you know that selectivity is actually length-based, but you're trying to work only in an age-based model, you get into some fairly horrible stuff. Anybody who can remember the deconvolution example from the closed-skin course, we want to stay away from that. So one thing is length makes it easier if you can assume that selectivity is at length, but not at age. The second is it's not relevant to animals that you're using as potential offspring or potential half sibs. Length doesn't really matter there. You just want to know how old they were. But for potential parents, you need to back calculate, you need to back project what their fecundity might have been at the time that the offspring might have been born or was born. So when you think about back projecting fecundity, you're really thinking about back projecting size, not age. With half siblings, it turns out that in the mechanics of the calculation, somebody said something about dwarves and giants yesterday. It does matter. If you're a small adult for your age, SBT, if you're 160 centimeters, or that is quite small, and you're 15 years old, you're still going to be small for your age when you're 25. And that has a sort of weird quadratic effect on the half sibling probabilities, slightly related to what John was asking earlier. So you need to be able to sum across the distribution of length, potential length at age, just in the mechanics of the half sibling probabilities. Again, there's a trick for doing this quite efficiently. But if you don't do that, you're going to hit about a 15% bias, which is in fact lurking within the SBT model at the moment, because I think that's purely age-based. Yep, it's primarily to do with fecundity and the need to project fecundity forward and backwards in time with close kin. But there's also a sort of benefit with the selectivity stuff. Over.
Thanks, Mark. Matthew, you got a question?
Yeah, I have a question about the genetics specifically. So if you're doing like a genetic sampling where you're testing with fewer base pairs, and then you take the samples that have putative half sibling or parent offspring pairs, and then you're doing a more extensive genetic testing with more base pairs to more further test to make sure that you have not false positives for those individuals. How do you account for the non-independence of those two samples and all those different pairings in a likelihood context if you're going to integrate those two separate data sets using the same individuals that were sampled into a integrated stock assessment?
I could respond on that, but Rich, I think you were going to follow up on the previous question. Is that right?
That's right. Mike, I suspect this is a debate we'll have till both of us check out or the first one checks out. But yeah, with the half sib one, I think that's true if every animal is going to be lifetime long or short. And there's some species that show that as almost systematic and some that don't. So if you look at the age recaptures of SBT, some of them do show the lifetime long short thing, where you're consistently above or below the size of age. Some of them don't, and that includes into adulthood. So I think there's an overcorrection possibility that what you said is true if every animal follows that, they have their individual L infinity, whatever, and they all share the K and the T0. But it's not that if every animal doesn't do that, or if a substantial portion doesn't do that, that would be an overcorrection. I don't know exactly how to solve this one, but with SBT and with quite a few other species, they don't all show that lifetime long short thing. So I think there's a bit more nuance to that, but man, we'll be talking about that for another 20 years, I suspect.
Yeah. We'll be mumbling into our pints of beer about this for a long time. I think the one thing is it only needs to be your expected future size that matters. Like if you're small for your age now, you're still a lot bigger than me, Rich. That doesn't seem to have changed over the years we've known each other. I don't think it's going to change now, but it's only the expected size that matters. For Matthew's question, well, what you want to do is throw plenty of SNPs at it. 3,500 is a great number, and you don't really have ambiguity about kin pairs, except between second and third order. You have to do something about it with this false negative stuff that Rich mentioned, but we kind of handle that. We do not. I don't advocate the practice of going back in and sort of adding more loci to check. It's just more economical and simple to throw 3,500 SNPs at it right now, and you get basically an unambiguous signal back. The models expect the only way to maintain sort of sanity in the models is to keep the computational down, is to take the genetic outcomes as basically definite, accepting there might be something like a tiny percentage of error, but that's not going to throw out estimates very much. So you really have to take them as definite rather than as things that have likelihoods that enter into the final calculation. So the identification of kin pairs is done as a preliminary step, and we stick a label on this pair and said, yep, it's definitely a POP, or it's definitely a second order kin pair, even accepting that the latter might be very slightly out. So, what's to say about that? It's much, much better to just spend the money on the genetics. It's not much, and get this stuff pretty definite. And then it's a yes, no in the model, and the code sort of behaves itself. Over.
Yeah. Matt, are you kind of thinking about the Atlantic red snapper situation?
Yeah.
No, that's so yeah, that was a situation where the folks started off with a GT-seq panel that they were hoping was going to have enough power to do stuff, but there was so much missing data in it that there really wasn't, what wasn't suitable for a single pass. And so then, yeah, they needed that confirmation step. And I would definitely, I agree with Mark that, do have enough SNPs in the very beginning so you don't have to do that. I mean, I'm of the mind now that if you can get the costs down enough, you can do low coverage whole genome sequencing and actually be even more precise about things. Although with a lot more bioinformatic work. But if that is the situation you find yourself in, there's a whole lot of work that has to go into calculating what the false negative rates are for different pairs in that particular initial screening with the somewhat underpowered GT-seq panel. And that, that accounts for missing the amount of missing data, and that's quite difficult. But then you can basically calculate an overall false negative rate, which is dominated by that initial screening step, but then also by the product with the other one. Now, as far as the non-independence between those two, because you've got the same pairs, so you might have, I'm trying to think, like you could have, things could be non-independent in the sense that, you might have had lots of missing data with the original screening of the pair, and consequently, because they had sort of poor tissue quality, poor DNA quality, and so that's going to also affect the DD-RAD section, or the sort of finer, more precise screening. But I'm not sure that non-independence is going to interfere with just being able to take a product of 1 minus the false negative rate in both cases. Does that answer your question?
Yeah,
Hello?
I guess I'm concerned that because you're using that same individual, you're double using your data in terms of how many actual pairs that you actually have, right? And
I don't think so.
Or I guess more in terms of how many actual samples you have, how many actual putative pairs you have, because you've used one individual twice in terms of how you've measured the genetics. And so maybe we can have this conversation.
Yeah, we can have this offline. I'd love to talk with you more about it, but it's the same number of pairs there. You just dump a whole bunch in the beginning. But yeah, I would love to talk more.
Yeah. Okay. Well, yeah, good conversation to have offline. So we've come to the end of the day. Thanks a lot, everybody, for your presentations and the discussions. And we start again tomorrow at 11 a.m. For the last day of the workshop, where we're going to, in the morning, cover length-based dynamics. So that's basically modeling age and length at the same time. And then talking a little bit about general concepts in terms of how to create a general model. And then at the end, we'll have a general discussion period where hopefully we can sort of outline some major decisions we have to make for this new model and get people's opinions on that. So thanks a lot, everyone, and we'll see you tomorrow.
All right. Thank you, Mark.